Why can't human eyes see the full range of light in the universe? How did William Herschel's prism experiment reveal invisible infrared light? What hidden features of space become visible when we look in infrared? We gaze up at the night sky, our eyes gathering the faint starlight that has travelled across the void. In this darkness, spangled with stars and the pale mist of the Milky Way, we trust what we see. But our sight is limited. Our eyes, marvellous as they are, perceive only a thin sliver of all the light that dances through the universe. The cosmos brims with light and other signals far beyond our eyes' reach. We are blind to so much more, yet for millennia we did not realize how much was hidden in that darkness. Imagine an early stargazer lying on cool grass long ago, under a clear velvet night. They watch the constellations slowly rise, breathing in the earthy chill and the scent of dew. For them, the twinkling lights above are all that exists out in the cosmos. The universe beyond Earth seems contained in those shimmering points overhead. As far as their eyes can tell, nothing else is there, just a silent darkness between the stars. It feels calm, eternal, and complete in its stillness. Centuries pass, with humanity guided by visible light alone. By day, the sun bathes the world in brightness. By night, the stars offer faint glimmers to navigate by. We learn to steer ships across oceans using those stars, to mark the passage of time by the sun and moon. Light was our guide and our comfort. But light, as we knew it, meant only what our eyes could see. Unknown to us, the sunlight warming our skin carried secrets we couldn't detect. The starlight reaching us was only a whisper of a much richer cosmic song, beyond the red hues of sunset and the violet of twilight. Invisible colours were waiting, entirely unseen by human eyes. For ages, these hidden forms of light danced just out of reach, quietly influencing our world. We felt their presence as the gentle heat on a sunny day, or noticed their subtle effects in mysterious ways, but we had no idea what they were. Our reality was constrained by our biology. Human eyes evolved to catch only a certain range of wavelengths, the rainbow from red to violet. Outside that narrow range, an infinite expanse of light went unnoticed. It's as if we had been living in a beautiful old house, but only ever explored one room of it, unaware of countless other rooms around us. We assumed that one room was the whole world, because it was all we knew. Now and then, hints of something more flickered at the edges of perception. We might feel the warmth of sunbeams through a window, even when the bright light itself is hidden. We might see the faint glow of coals long after a fire has burnt down, warmth lingering in the darkness. These were clues, signs that light was not just what our eyes could see, or what visibly illuminated objects. Still, for a long time, such clues remained unexplained mysteries, little curiosities in daily life. In nature, some creatures experienced a reality beyond our sight. Bees, for instance, navigate by colours we cannot see. On a bright summer day, a flower that looks plain to us might blaze with patterns under ultraviolet light, a secret guiding map on its petals visible only to the bee's eyes. Many birds, too, have ultraviolet vision, making their plumage far more colourful to each other than what humans perceive. And in the cool desert night, a snake hunting for prey senses the heat of a mouse as a radiant glow in the darkness, effectively perceiving the infrared warmth of its body. These animals move effortlessly in unseen worlds of light, while we humans remained oblivious that such worlds even existed around us. Slowly, our curiosity grew. We began to ask, are there kinds of light our eyes miss entirely? If the sun can warm us through a pane of glass, even when we stand in the shade, could there be invisible rays carrying that warmth? If certain chemicals change, or certain creatures respond to light we can't see, what does that mean? The stage was set for discovery. Our understanding of light, and of the universe, was about to expand in ways that would forever change how we see our world. In the quiet dawn of a new century, experiments would reveal the invisible. We stood on the brink of unveiling a hidden spectrum that had been there all along. A spectrum that would open our eyes beyond the limits of our natural sight and unlock deeper secrets of the cosmos. The journey into the unseen was about to begin, and with it, a richer and more mysterious universe would unfold before us. It was in the early 19th century when the first hint of these invisible lights was uncovered. Picture a sunny room in the year 1800. A shaft of sunlight streams through a small opening, passing into a glass prism and fanning out into a painted ribbon of colours across a tabletop. Vivid red fades into orange and yellow, then green, blue, and violet. Newton's rainbow splayed out before curious eyes. At the table, an astronomer named William Herschel carefully moves a thermometer through each band of colour, measuring the warmth of each hue. Red, orange, yellow. Each gives a temperature reading. He notices the thermometer creeps higher under the red light than under the green, and higher in green than in blue. That makes sense. Red light has always felt warmer to him than blue light. But Herschel wonders, does the warmth continue beyond the visible colours? He decides to measure just beyond the red band of light, in a region where to his eyes there is nothing at all, only an empty space on the table beyond the visible spectrum. Gently, he places the thermometer just past the glowing red edge. To his amazement, the thermometer begins to register an even higher temperature there, beyond the red light, in the darkness. It is as if the darkness itself carries warmth. Perplexed and intrigued, he double-checks his setup, moving the thermometer in and out of the visible rainbow. Each time, he finds consistently that an unseen form of light, one he cannot see with his eyes, is falling beyond the red end of the spectrum, warming the thermometer even more than the red light did. This is a profound discovery. Sunlight contains an invisible ingredient, a type of light that we cannot see but can feel as heat. Herschel has discovered infrared radiation, named for being below red. It is a silent light, a warmth that permeates the world without ever stirring the colours of the eye. For the first time, humanity has proof that there is more to light than meets the eye. One can imagine Herschel's quiet excitement at this realization. In that beam of sunlight, something invisible, yet undeniably real, is present and measurable. The world suddenly seemed a little less dark in the places we once assumed were empty darkness. News of Herschel's discovery spread through the scientific community, expanding their view of nature. The apparent boundary at the red end of the rainbow had been crossed, revealing that even sunlight, so ordinary and constant, held surprises beyond the reach of vision. They called these new rays calorific rays at first, for the heat they carry. Later, the term infrared comes into use. We come to understand that infrared is essentially the light of heat. Any object that is warm, a sunlit rock, a living human, or a distant planet, glows in infrared light, even if it appears dark to our eyes. In a sense, Every warm thing has an aura of heat radiating out, painting the space around it with invisible light. On a chilly night, if you hold your hand near a brick wall that soaked up sun during the day, you can feel warmth wafting from it in the darkness. That is infrared light whispering to your skin. As our knowledge grows, we learn that infrared light is all around us. Even in complete darkness, the world is not truly dark if one can see infrared. A cat prowling in the midnight hour, or a person standing alone in a moonless field, still emits a faint glow of heat. Before long, inventors devise special instruments and cameras that can detect this glow. Through these infrared eyes, we gain the ability to see warm bodies moving in the night, to find lost people in dark forests by their heat signatures, or to watch wild animals prowling under the cover of darkness. Firefighters learn to see through smoke using infrared imaging, spotting people and flames hidden to normal sight. The invisible becomes visible in shimmering shades of warmth. When we turn these new eyes to the sky, a hidden cosmos emerges. The night sky that to our eyes is sprinkled with stars and framed by blackness is, in infrared, aglow in unexpected ways. Cool clouds of dust that drift between the stars, utterly opaque to visible light, begin to shine in infrared like ghostly silhouettes made of warmth. In these clouds, newborn stars are wrapped in dusty cocoons. They cannot be seen in ordinary light, but with infrared telescopes, we can peer through the dust and witness the gentle glow of stellar nurseries where new suns are coming to life. Entire structures at the center of our galaxy, veiled behind thick dust lanes that block visible light, are revealed in infrared images as glowing tapestries of warm gas and densely packed stars. It is as if a veil has been lifted from our view of the cosmos, revealing a scene that was there all along, but hidden behind dust and darkness. Infrared light also allows us to observe planets and other cool, dim objects in space that shine too faintly in visible light. The subtle warmth of a planet, like Jupiter or Saturn, for instance, can be seen in infrared, showing us details of their cloud bands and storms, even on their night side, which our eyes would see as dark. We can detect the heat of moons, asteroids, and comets, mapping their sunlit and shadowed regions. Even distant exoplanets orbiting other stars, nearly impossible to spot in visible light because of their star's glare, betray themselves in the infrared, either by the faint heat they glow with, or by the way they momentarily dim their star's infrared light when passing in front of it. Bit by bit, infrared opened a new window on the universe, letting us sense the heat of worlds and nebulae light years away. Today, some of the most powerful observatories, orbiting high above the Earth, are designed specifically to capture infrared light. They peer deep into dusty galaxies and back in time toward the faint dawn of the universe, seeing the heat of the first stars and galaxies that formed, a sight completely invisible to our unaided eyes. And to think, all of this sprang from that simple experiment with a prism and a thermometer. One moment of curiosity in a sunbeam unveiled an entire spectrum that had been hiding in plain sight. Infrared light had been present every day in sunlight and starlight, warming our skin, baking the ground, shaping weather and climate. Yet we had never seen it. Now, not only do we know it is there, we have learned to harness it. We can finally light up the dark with a new kind of gentle vision, one that does not rely on the eyes we were born with, but on eyes of our own invention. As remarkable as this is, the revelation of infrared was only half of a greater story. Herschel's findings immediately raised a tantalizing question. If an invisible form of light existed beyond red, might there also be invisible light beyond the other end of the rainbow, beyond violet? It did not take long for the answer to emerge. Just a year after Herschel's breakthrough with infrared, another door into the invisible was about to open. In 1801, on the other side of the spectrum, attention shifted to beyond the violet end of visible light. A young German scientist named Johann Wilhelm Ritter had heard of Herschel's discovery and wondered, if invisible rays exist beyond red, might there also be something beyond violet? At the time, scientists knew that certain chemicals, like silver salts, darken when exposed to sunlight. Ritter decided to use this chemical reaction as a detector for any invisible light. He set up a prism to cast a rainbow spectrum of sunlight onto a table, much like Herschel had done. But instead of thermometers, Ritter placed strips of paper coated with silver chloride along the spread of colours. Silver chloride is sensitive to light. It starts off white, but turns dark when it soaks up enough sun. As expected, the paper strip in the blue part of the spectrum darkened more than those in the red. The violet end darkened even more, since violet light carries more energy. Then Ritter took another prepared strip and placed it just beyond the violet edge of the visible spectrum, where no sunlight was visible to his eyes at all. If nothing existed there, the chemical-coated paper should remain unchanged, as if it were in the dark. For a short while, nothing happened. But as Ritter waited patiently, he began to notice the paper beyond violet was indeed turning faintly darker, as if an invisible ink were revealing itself. Excited, he exposed it a bit longer, and the effect became clearer. The strip just beyond the violet was darkening, even though no visible light shone on it. There was, in fact, something beyond violet, an unseen light that could trigger a chemical reaction. Ritter had discovered ultraviolet radiation, the light beyond violet. Just as Herschel's invisible rays carried heat, Ritter's invisible rays carried energy capable of inducing chemical changes. Initially, these strange new rays were called oxidizing rays, or chemical rays, because of their effect on silver compounds. Later, they would be named ultraviolet. The existence of ultraviolet light was another profound expansion of our view of nature. It soon explained a few lingering mysteries. For example, it clarified why sunlight could burn and tan our skin. The warmth of the sun, largely from infrared and visible light, is pleasant, but the sunburns and deep tans come from the invisible ultraviolet rays that Ritter had revealed. Those rays carry enough energy to trigger chemical changes in skin cells, and in high doses they can damage tissue. Humans had felt their effects long before. Anyone who spent a summer day outside and ended up sunburnt had encountered an invisible agent of change. But now we finally knew the cause. Ultraviolet light was a hidden aspect of sunshine, one that had been acting on us and the natural world unseen. To scientists of that era, it was as though the sun had been writing in invisible ink all along, leaving its mark on skin and chemicals without anyone realizing, until Ritter's experiment revealed the secret. Ultraviolet soon showed itself in other surprising ways. Certain minerals and materials, when exposed to ultraviolet, would glow with visible colors, a phenomenon called fluorescence. People found that by shining UV black lights on rocks, plants, or even paintings, they could reveal eerie luminescent patterns. For instance, some common rocks will emit a ghostly glow of greens or oranges under ultraviolet light, even though they look ordinary under normal illumination. Even some living creatures have secret patterns revealed by ultraviolet. The wings of butterflies and the feathers of certain birds carry ultraviolet markings visible only to animals with UV vision. Under moonlight, a scorpion scurrying in the desert appears drab and hard to see. But under ultraviolet light, it shines a brilliant blue-green, as if painted with a hidden neon ink. These dazzling effects were tangible proof that a light we cannot see directly was nevertheless all around us, capable of making other things glow in reply. It was like discovering a hidden alphabet in which nature could write, visible only when read with ultraviolet eyes. As with infrared, once we developed instruments to sense ultraviolet directly, we turned them toward the sky and discovered new wonders. The sun, viewed in ultraviolet, looked very different from the familiar yellow-white disk. Through UV telescopes, the sun's surface and atmosphere seethed with activity. We saw enormous loops of gas arcing above the sun's limb and patches of turmoil where solar flares erupted, all bright in ultraviolet. The normally invisible high-energy face of our star was revealed, showing the sun's magnetic violence in stark detail. And beyond the sun, the universe was brimming with ultraviolet light from countless sources. The hottest and most massive young stars flood their surroundings with intense ultraviolet radiation. This high-energy light causes nearby clouds of gas to glow in vivid colors, once the gas re-emits the energy as visible light, creating beautiful nebulae around clusters of newborn stars. When we observe star-forming regions with ultraviolet detectors, we see a wealth of structure that was invisible before. Dark patches of sky come alive with activity. Areas that looked empty now show themselves filled with hot, brilliant young suns and the fluorescent haze of the gases they excite. Even galaxies have secret lives in ultraviolet. A galaxy that appears calm in visible light might reveal regions of frenzied starbirth along its spiral arms when seen in ultraviolet, as though a special lamp has exposed where new stars are coming to life. The dazzling cores of distant galaxies known as quasars also shine intensely in ultraviolet, a telltale sign of the extreme energies released around their central black holes. All these sights impressed upon astronomers that the universe had a high-energy side, teeming with events and objects we'd long missed. However, observing the ultraviolet universe from the ground proved difficult. Our planet's atmosphere, thankfully, absorbs most of the incoming ultraviolet from space. High above in the stratosphere, a thin layer of ozone gas acts as a protective shield, filtering out the majority of the sun's harmful UV rays before they reach the surface. Without this defense, life on Earth would suffer greatly under the sun's harsh ultraviolet light. But this same protective blanket that keeps us safe also blinds our ground-based telescopes to most ultraviolet light from the stars. To truly explore the UV sky, we had to get above the atmosphere. Starting in the mid-20th century, scientists lofted ultraviolet detectors on high-altitude balloons, then on rockets that briefly soared above the atmosphere, and eventually on satellites orbiting Earth. When these instruments finally achieved unobstructed views of the ultraviolet cosmos, a new landscape came into focus. They saw brilliant young star clusters blazing with ultraviolet light, galaxies with energetic cores emitting UV flashes, and the ghostly shells of supernova remnants glowing with a fierce ultraviolet sheen as shockwaves from long-ago stellar explosions heated the gas. The universe seen in ultraviolet became a place of high energy and youthful vitality, a realm of hot stars and dramatic cosmic events that had been hidden from our eyes until we developed the means to see them. By the mid-19th century, the discoveries of infrared and ultraviolet had radically broadened our concept of light. No longer was light confined to the rainbow we see. These invisible rays were recognized as part of a continuous spectrum, an electromagnetic spectrum that extended far beyond the colors familiar to human sight. We began to realize that visible light was just a small window in an immense expanse of radiation. It was like learning that the tiny island we live on is part of a vast continent we had never explored. Scientists started to speculate. If infrared and ultraviolet are just two ends of this spectrum, how far does it extend? Are there even longer waves beyond infrared, or shorter, more energetic waves beyond ultraviolet? What might those reveal about the world and the cosmos? The quest to uncover the full extent of light had truly begun. Indeed, in the late 19th century, a physicist named James Clerk Maxwell would provide a theoretical framework uniting electricity, magnetism, and light, and predicting the existence of many more invisible wavelengths beyond infrared and ultraviolet. As the 19th century gave way to the 20th, our theoretical understanding of light caught up with these discoveries, paving the way for detecting an entire rainbow of invisible light stretching far beyond human sight. By the late 1800s, scientists began to see a pattern linking all these forms of light. The discoveries of infrared and ultraviolet hinted that they might be part of a much broader continuum. This suspicion was confirmed by a brilliant physicist named James Clerk Maxwell. In the 1860s, Maxwell developed equations that wove electricity, magnetism, and light into a single theoretical framework. His calculations suggested that visible light was just one segment of a vast spectrum of electromagnetic waves. Notably, the speed at which his theoretical waves would travel came out to about 300,000 kilometers per second, the very speed of light, strongly suggesting that visible light itself was just one form of electromagnetic wave. According to Maxwell, there could be waves much longer than infrared and much shorter than ultraviolet, all obeying the same fundamental laws. It was a revelation in thought. The rainbow we see is but a tiny slice of what is possible. There were invisible colors beyond red and violet, extending far in both directions, potentially without end. It didn't take long for Maxwell's prediction to be proven right. On the long-wave end of the spectrum, beyond infrared, came the discovery of radio waves. In 1887, a German physicist named Heinrich Hertz conducted experiments to test Maxwell's theories. He set up an apparatus that could generate fast electrical oscillations and another device across the lab to detect them. When he turned the system on, he observed that an invisible wave was indeed traveling from the transmitter to the receiver, even through obstacles. These were radio waves, far longer in wavelength than any light known before. Hertz found that they behaved just like light. They could be reflected, focused with mirrors, and produced interference patterns. Though Hertz was simply exploring a curiosity of physics, his work opened the door to an age of wireless communication. Soon inventors like Guglielmo Marconi seized upon radio waves to send signals across great distances without wires. By the turn of the 20th century, radio waves were being used to transmit Morse code across the Atlantic. Unknowingly, humanity was not just inventing a new means of communication, but also opening new ears to the cosmos. Even as early radio towers began to dot the landscape, the sky above was full of radio waves, traveling alongside the visible starlight, unnoticed. All we needed were receivers tuned to those frequencies to begin hearing the universe in a new way. In the 1930s, the first hint of cosmic radio waves was detected. An engineer named Karl Jansky was investigating static interference in radio communication for a telephone company. He built a large rotating antenna and listened to the faint natural radio hiss coming from different directions. Among the crackles of thunderstorms and random noise, Jansky found a persistent signal that peaked every 23 hours and 56 minutes. The length of a sidereal day, the rotation period of Earth relative to the stars. This timing told him the signal was coming from space, not from some local source. He eventually pinpointed it to the direction of the constellation Sagittarius, toward the center of our Milky Way galaxy. Jansky had discovered that stars, or something at the galactic center, emitted radio waves. It was a quiet revelation. The universe was speaking in radio all this time, and we had just begun to listen. At first, this discovery did not receive much attention. It was the midst of the Great Depression, and Jansky's work was seen as a telecommunications curiosity. But a few years later, another radio pioneer, Grota Rieber, built a dish-shaped antenna in his backyard, essentially the first radio telescope, and started systematically surveying the sky in radio frequencies. He confirmed that the Milky Way glowed in radio waves and mapped out stronger sources here and there in the sky. Thus was born radio astronomy, an entirely new way to observe the cosmos. As the decades went on, astronomers constructed larger and more sensitive radio telescopes, listening to the sky with ever greater clarity. They discovered that the calm night sky of stars conceals a bustling radio universe. In radio waves, the sun can be a crackling source of bursts during flares. Some objects, like certain nebulae, shine more brightly in radio than in visible light. Enigmatic new phenomena were found. Quasars, distant galaxies blazing with the light of matter falling into giant black holes, pouring out torrents of radio energy. Pulsars, the rapidly spinning remnants of supernova explosions, ticking out precise radio pulses like cosmic clocks. Even the tenuous gas spread between the stars could be sensed through its faint radio emission, such as the gentle 21-centimeter line from neutral hydrogen, which allowed us to trace the structure of our galaxy's spiral arms. Every advance in radio astronomy revealed a universe that our eyes alone could not perceive. What looked like empty space in a photograph might be alive with radio signals from colliding galaxies or the remnants of exploded stars. With these new ears, we were eavesdropping on the cosmos, catching the stories carried on invisible waves. One could say that we were not just seeing the universe now, but hearing it for the first time, tuning in to cosmic stations on a radio dial. If those signals were transformed into audible sound, they might be heard as a faint, steady hiss, or perhaps a slow, rhythmic beep, the heartbeat of a distant pulsar echoing across space. By the mid-20th century, radio astronomy had unveiled a previously unseen cosmos on the long-wave end of the spectrum. Meanwhile, other scientists were setting their sights on the opposite, short-wave end of the spectrum, where entirely new phenomena were soon to be revealed. While scientists were exploring the long, gentle waves of radio, others turned their attention to the opposite extreme of the spectrum, beyond the violet, where wavelengths grow incredibly short and energies incredibly high. New kinds of light were waiting to be discovered. In 1895, a German physicist named Wilhelm Röntgen was experimenting in a darkened laboratory with cathode ray tubes, glass tubes from which air had been pumped out, through which he passed electrical currents. To his surprise, a barium platinocyanide screen sitting nearby began to glow, even though it was not in the direct path of any visible beam. Something invisible was emanating from his apparatus and causing the screen to light up. Röntgen found that this unknown ray could pass through materials that light normally could not. He famously took an X-ray photograph of his wife's hand. In the image, her bones and even her wedding ring were clearly visible, while the flesh appeared ghostly transparent. It was a strange and marvelous sight, as if seeing a shadow of the invisible. Not knowing what else to call this mysterious new radiation, he named it X-rays, with X representing the unknown. Before long, the news of X-rays spread worldwide and captured the public's imagination. Doctors realized they could peer inside the human body without a single incision, and within months, X-ray machines were being used in medicine. Scientists, meanwhile, pondered what X-rays really were, and soon guessed correctly. They were a form of light, but with wavelengths far shorter and energy far higher than even ultraviolet. X-rays were an extension of the electromagnetic spectrum on the short wavelength side, just as radio waves were an extension on the long side. Here was yet more proof that Maxwell's spectrum was real and vast. Visible light was just a sliver sandwiched between infrared on one side and X-rays on the other, with ultraviolet bridging toward the X-ray side. A few years after Röntgen's discovery, researchers uncovered another new emission, this time from naturally radioactive materials like uranium. These rays were even more penetrating than X-rays. By 1903, scientists Ernest Rutherford and Paul Villard had categorized radiation from such materials into three types: alpha and beta particles, and a highly energetic neutral radiation, which Villard named gamma rays. Gamma rays, it turned out, are another form of electromagnetic radiation, with even shorter wavelengths and higher energy than X-rays. They represent the extreme high-energy end of the spectrum. For a long time, X-rays and gamma rays were studied mostly in laboratory settings and known for their medical or atomic uses. Scientists could produce X-rays with electrical tubes and gamma rays from radioactive substances. But who would have imagined that nature was producing them in great quantities far away in space? As we entered the mid-20th century, we began to find out. Just as Earth's atmosphere blocks most ultraviolet light, it also blocks virtually all X-rays and gamma rays from space. A fortunate shield for life on Earth, but a hurdle for astronomers eager to explore the high-energy universe. It was only with the advent of rockets and space exploration that we could finally open our eyes to X-rays and gamma rays coming from beyond our planet. In the late 1940s and 1950s, rocket-borne detectors confirmed that the sun emits X-rays, especially during solar flares when the sun's surface erupts violently. Then in 1962, an experiment launched on a rocket discovered the first cosmic X-ray source outside our solar system, a point of intense X-ray emission in the constellation Scorpius. This source, later dubbed Scorpius X1, turned out to be something extraordinary, likely a neutron star or black hole feeding on a companion star, generating X-rays as gas was heated to extreme temperatures. It was the first clue that the universe was brimming with X-ray activity in places we hadn't suspected. As X-ray observatories were lofted into orbit in the following decades, the high-energy sky came into view. Astronomers found that certain remnants of exploded stars, like the famous Crab Nebula, shine brightly in X-rays as electrons whirling in magnetic fields give off high-energy light. Entire clusters of galaxies were discovered to be enveloped in enormous clouds of superheated gas, emitting X-rays, revealing previously invisible structures binding galaxies together. And supermassive black holes at the centers of galaxies, dark invisible light, were seen churning up gas and lighting up the universe in X-ray energies. The cosmos viewed in these rays was violent and energetic, sites of cosmic explosions, collisions, and intense gravity. Gamma-ray astronomy also took off in the late 20th century. In the 1960s, satellites designed to monitor nuclear bomb tests on Earth serendipitously found brief, intense flashes of gamma rays coming from deep space. These gamma ray bursts, as they were called, were unlike anything seen before. They lasted only seconds to minutes, but in those moments, they emitted more energy than many stars do in their entire lifetimes. It was later determined that they signaled cataclysmic events, the collapse of massive stars, or the mergers of neutron stars in distant galaxies. Apart from bursts, astronomers also detected a faint gamma-ray glow permeating space, produced by cosmic rays striking interstellar matter and by the decay of radioactive elements created in stellar explosions. By the dawn of the 21st century, humanity had finally spread its observational net across the full electromagnetic spectrum, from the longest radio waves to the shortest gamma rays. We were tuning in to the cosmos on all channels. Each portion of this spectrum opened a unique window onto the universe's story. Through radio waves, we perceived calm, cold clouds of gas and mapped out the grand structure of galaxies. In infrared light, we detected warm dust and newborn stars hidden behind veils of darkness. Ultraviolet views revealed energetic young stars and hot stellar nurseries, glowing with high-energy light. X-ray observations showed us violent explosions and exotic objects like neutron stars and black holes, cutting through the galaxy's dust to expose cosmic catastrophes. And at the extreme, gamma rays unveiled the most cataclysmic events of all: titanic bursts and the furious workings of matter under the greatest energies. Together, these once invisible parts of the spectrum became essential to painting a complete picture of the cosmos. In 1965, a chance discovery using a microwave antenna revealed something astonishing. The universe itself was aglow with the faint afterglow of its beginning. At a laboratory in New Jersey, two radio astronomers, Arno Penzias and Robert Wilson, were working with a large horn-shaped microwave antenna. They intended to use it to study faint signals from the space between galaxies. But an unexpected noise plagued their measurements. No matter where they pointed this sensitive antenna, it picked up a low, steady hiss of microwave static. It was present day and night in every direction, and it persisted despite their best efforts to eliminate it. To their ears, it was just an unchanging, faint noise, simple static with no obvious source. Puzzled, Penzias and Wilson checked every possible source. They even discovered that pigeons had roosted in the antenna, leaving droppings. Suspecting this might be the cause, they cleaned the antenna thoroughly and gently shooed the birds away. Yet the mysterious noise remained. What they had found, quite by accident, was nothing less than the faint glow of the early universe. At the same time, a team of physicists not far away had predicted that if the universe began in a hot Big Bang, the tremendous light from that birth should still be around, cooled and stretched by billions of years of expansion into a cold, diffuse microwave glow. Penzias and Wilson's persistent hiss turned out to be this very glow, the cosmic microwave background radiation. It is the oldest light we can observe, a remnant from when the universe was only 380,000 years old and had just become transparent. Back then, the entire cosmos was a blaze of energetic light. Over nearly 14 billion years, that blaze has cooled to a whisper, now just a few degrees above absolute zero, filling space like a dim afterglow of creation. This discovery was a milestone in our cosmic journey. In one stroke, it provided compelling evidence that the universe began in a hot, dense state, the Big Bang. And it showed that the seemingly dark sky around us is actually aglow with a uniform microwave light from all directions. To our eyes, this light is invisible and extremely faint. We don't feel or see it, But with a microwave antenna, the entire universe lights up with this soft background radiation. It is as though the cosmos carries a memory of its fiery birth, now cooled and gentle, a whisper from the dawn of time. The cosmic microwave background, often called the CMB, quickly became a cornerstone of modern cosmology. Scientists were eager to map it and tease out the information hidden in its faint ripples. Over the next few decades, instruments on balloons and satellites were launched above Earth's atmosphere to measure the CMB across the sky. These maps showed that the microwave background is almost uniform, but not perfectly so. There are minuscule variations in temperature, mere fractions of a degree, from one spot to another. When visualized, it looks like a mottled pattern of tiny hot and cold patches, a bit like a speckled pastel painting wrapping the entire sky. Those slight variations in the CMB are tremendously important. They are the imprints of ancient sound waves and density fluctuations in the primordial universe. Where the CMB is a hair warmer, there is a bit more matter. Where it's cooler, a bit less. In time, the denser spots would grow into galaxies and clusters of galaxies, while the emptier spots would become vast cosmic voids. In this way, the CMB maps have been like a baby picture of the universe, allowing scientists to discern its age, ingredients, and early behavior. Yet amid these subtle patterns, one feature stood out, puzzling researchers. In the southern sky, a particularly large region appeared to be slightly cooler than the average CMB temperature by more than the usual amount. This area, spanning several degrees of the sky, far larger than the full moon's disk, was soon nicknamed the cold spot. Compared to the typical tiny fluctuations in the CMB, this cold spot was an oddball, notably colder and larger than expected. Scientists proposed various explanations. One possibility was that a colossal void in the relatively nearby universe, an enormous region mostly empty of galaxies, lay in that direction, and that this void sapped a bit of energy from the CMB photons passing through it, leaving them cooler when they reach us. Indeed, surveys did find something of a deficit of galaxies in that general area of the sky, suggesting a huge void. But it's still unclear whether that void is truly large and deep enough to explain the cold spot entirely. Another idea ventured into more exotic territory. Perhaps the cold spot is a bruise from an ancient collision between our universe and another bubble universe in some larger multiverse. In such speculative theories, if another universe had once grazed ours, it might have disrupted the uniform glow of the CMB, leaving an unusual cold region. This idea is far-fetched and difficult to test, but the mere fact it was considered shows how mysterious the cold spot seemed. Of course, it's also possible that the cold spot is simply a statistical fluke, an unlikely, but not impossible, random variation in the cosmic noise. As scientists collected more precise data with the Planck satellite in the 2010s, the cold spot's significance was somewhat reduced, meaning it might not be as inexplicable as initially thought. Still, it remains a curious anomaly. What the cold spot undeniably provides is a reminder that even with our comprehensive understanding of the cosmos, there are still puzzles out there. We have peeled back so many layers of the invisible spectrum and uncovered the grand story of the universe's evolution. Yet here and there we encounter features like the cold spot that make us stop and ponder. Our journey through the unseen spectrum illustrates how each time we extend our senses, the cosmos rewards us with wonders. From the warmth of infrared to the energy of ultraviolet, from the long whispers of radio waves to the ancient glow of the cosmic microwave background, we have uncovered layer upon layer of reality that was always there, just beyond our sight. In scarcely more than 2 centuries, a blink of an eye in cosmic time, humanity transformed its view of the universe. We went from gazing at a sky of only stars and darkness to realizing that the sky is rich with hidden light and sound, a whole symphony of electromagnetic waves singing and shining around us all the time. It's humbling and inspiring to recognize how much was concealed in the darkness all along. What we perceive directly is only a fragment of what exists. There is an entire cosmos of phenomena that our limited eyes and ears can easily miss. Yet those phenomena surround us and influence us every day. Even now, the air around you carries a complex chorus of radio waves, the quiet hiss of distant stars and nebulae, the faint echo of the Big Bang, and even the signals of human communications, all intertwining in an inaudible song. Your own body emits a soft infrared glow, a gentle warmth that dissipates into the night. High above, the sky we call dark is actually bright in other wavelengths. It is awash in the microwave afterglow of creation and dotted with occasional X-ray or gamma-ray flashes from far-off cosmic events, though we remain oblivious to them without our instruments. So as you lie under the night sky, imagine it. All that invisible light raining down and passing through you. No longer is the night empty. It is filled with the invisible starlight of countless suns and galaxies, and the echoes of the universe's birth. Every patch of dark sky overhead is, in truth, bright at some wavelength. Perhaps it glows in microwaves from the Big Bang, or in infrared from a cloud of dust where new stars are forming, or in radio waves from a distant quasar. We are bathed in this sea of light beyond sight, an ocean of energy that we only learned how to perceive in very recent times. This realization does not make the night less beautiful or less soothing. If anything, it adds depth and wonder to its beauty. Knowing that the darkness is not empty at all, but rather hiding countless forms of light, can give us a comforting sense that we are not alone in the dark. Even when you close your eyes, warmth on your skin and the faint sounds of the world hint at realms beyond the visible. We remain cradled in these invisible fields of light and energy that have been present since the dawn of time. The cosmic cold spot, that peculiar patch of cooler glow in the sky, remains as a gentle mystery, a signpost reminding us that there is more to learn. Whether it turns out to be a statistical quirk, the imprint of a giant cosmic void, or something as fantastic as the touch of another universe, it has sparked imagination and continued inquiry. It whispers to us that the universe has not revealed all its secrets. For every question we answer, new ones emerge. As we conclude this exploration of hidden light, take a moment to simply feel the night. Envision the vast, invisible spectacle above and around you. Picture the entire spectrum of silent light that bathes the world. The residual warmth shimmering from the day's sunlight, still emanating from walls and roads in infrared. The gentle rain of radio waves that passes effortlessly through buildings and bodies, carrying messages and cosmic whispers alike. The soft glow of the cosmic microwave background, an all-pervasive blanket of ancient light draped over the sky. Sense that you are a part of this grand, ongoing exchange between the universe and everything within it. Under the canopy of stars, we find not only the visible constellations that have guided us for ages, but also the quiet presence of myriad unseen rays, each with its own story. Our ancestors looked up and felt wonder at the few thousand points of light they could see. Today, with all we have learned, the wonder has only grown. The night has become even more magical in our eyes. In the stillness of the dark, enveloped by both the stars we see and the light we cannot, we can drift to sleep, feeling profoundly connected to the vast cosmos. we can rest in comfort, knowing that the universe, in all its mystery and grandeur, watches over us in every wavelength of light, from the brilliant visible stars to the gentle, invisible glow of creation's afterglow. In this gentle darkness, alive with invisible light, our story comes to a close, not with a definitive answer, but with a question and a promise. The question is, what other wonders remain hidden, waiting for eyes or instruments yet to be invented? Already, we have begun to sense the universe in new ways beyond light. For instance, detecting the faint ripples in spacetime from distant cosmic collisions, known as gravitational waves. These achievements hint that even beyond the electromagnetic spectrum, there are messages in the cosmos for us to receive. And the promise is that as long as we continue to look deeper and dream bigger, the universe will continue to reveal itself to us, piece by piece, in light, visible and invisible. Each discovery, like a new star appearing in the sky, will guide us forward through the cosmic night, ever onward in our journey of understanding. Beyond the narrow band of colours our eyes can see, the universe is alive with invisible waves of light. In the silent darkness of a starry night, countless signals course through space, undetected by human vision. For centuries, astronomers peered through optical telescopes and charted the heavens by starlight alone. But as our curiosity grew, we learned that the cosmos speaks in many voices, many frequencies, and we had been listening to only one small octave of its symphony. It was a revelation to discover that light extends far beyond the familiar rainbow. In the early 19th century, the astronomer William Herschel found that warmth itself is a form of light just beyond red, what we now call infrared. Shortly after, Johann Ritter discovered invisible rays beyond violet, later named ultraviolet. Scientists soon realized the spectrum might stretch further in both directions. Decades later, James Clerk Maxwell's theory of electromagnetism revealed that visible light is merely one slice of a vast continuum of electromagnetic waves. In the 1880s, Heinrich Hertz confirmed Maxwell's prediction by generating radio waves in the laboratory, proving that these unseen waves behaved like light. Still, it would take until well into the 20th century for anyone to detect such waves coming from the stars. One of the most profound leaps in exploring these invisible realms came by accident in the early 1930s. On a quiet summer night, a young radio engineer named Carl Jansky was crouched beside a strange rotating antenna in rural New Jersey. He had been tasked with hunting down sources of static that interfered with transatlantic radio communications. Night after night, his tall, wagon wheel-like antenna swung slowly around, listening to the hiss and crackle of the atmosphere. Most of the noise he picked up came from thunderstorms or the sun. But Jansky noticed something odd, a faint signal that rose and fell each day, not with the 24-hour rhythm of the sun, but with a period roughly 4 minutes shorter. Puzzled, he realized this mysterious static wasn't following the sun's timetable at all. It was synced with the stars. Jansky traced the repeating hiss to a fixed point in the sky. As he analyzed the pattern, he determined it reached its peak whenever his antenna pointed toward the constellation Sagittarius, toward the dense heart of the Milky Way. In 1932, Jansky announced a stunning discovery. Radio waves were emanating from an extraterrestrial source, in fact, from the center of our own galaxy. This was no man-made interference, no earthly lightning storm. It was a signal from the stars themselves, an invisible broadcast from deep space. With that announcement, Jansky inadvertently founded a new science, radio astronomy. He had opened our ears to the cosmos beyond visible light. At first, Jansky's revelation was met with curiosity, but little immediate action. The idea of listening to the stars on radio waves seemed far-fetched to many of his contemporaries. Jansky's employer, Bell Laboratories, ultimately moved him to other projects, and the discovery might have languished. But a few enthusiasts were captivated by the possibility. One was Grota Rieber, a young amateur astronomer in Illinois. In 1937, Rieber built a large metal dish antenna in his backyard, looking for all the world like a giant steel saucer, and set about where Jansky left off. Night after night, Rieber aimed his homemade radio telescope at the sky, patiently mapping the intensity of radio signals across the heavens. Rieber's perseverance paid off. By the late 1930s and early 1940s, he had detected strong radio hotspots in the sky. There was an intense source in Cygnus and another in Cassiopeia, places where there were no obvious bright stars to explain them. He also found that the Milky Way itself glowed faintly in radio frequencies, especially toward its crowded center. Rieber published the first crude map of the radio sky, revealing that the universe had been transmitting on these invisible channels all along, even if our ears had not been tuned to listen. When World War II ended, the techniques of radar, developed for military purposes, were repurposed by scientists to probe the sky. In the post-war years, radio astronomy blossomed into a full-fledged field. Across the world, enormous parabolic antennas rose from the landscape, their metal surfaces gleaming under sun and stars alike. In remote valleys and high plateaus, these giant listening devices slowly pivoted and tilted, day and night, collecting whispers of radio energy from the cosmos. Unlike optical telescopes, they were unhindered by clouds or daylight. A radio dish can just as easily observe at high noon or through a cloudy night. Where an optical astronomer saw darkness, a radio astronomer could discern the subtle hum of atoms and the crackle of energetic galaxies beyond view. As multiple radio antennas sprang up, scientists learned to link them together as one giant ear, a technique called interferometry, to sharpen their view of the radio sky. By combining signals from antennas spaced far apart, they could pinpoint radio sources with unprecedented precision. This approach would eventually allow astronomers to capture extraordinary detail, even laying groundwork for imaging things as elusive as a black hole's shadow, though that triumph lay decades in the future. In those early decades, the focus was simply on finding and understanding the new cosmic phenomena that radio waves revealed. Radio observations soon unveiled features of our own galaxy that had been invisible to the eye. In 1951, astronomers detected a faint radio whisper at a wavelength of 21 centimeters, emission from neutral hydrogen atoms. Mapping this radio emission across the sky, they traced the structure of the Milky Way. For the first time, humanity could see the spiral outline of our galaxy from within, even though vast clouds of interstellar dust block those spiral arms from optical view. Radio waves pierced through that dust, unveiling the graceful swirl of our home galaxy and showing that it was far larger and more complex than the starry band we see overhead. The galactic center, which lies hidden behind opaque dust clouds, emerged in the radio as a brilliant source. In the 1950s and 60s, radio astronomers discovered a strong, compact signal right at the core of the Milky Way. This was a clue that something extraordinary lurked there, something generating prodigious energy. Decades later, we would come to understand that a supermassive black hole resides at the galaxy's core, and that the radio emission comes from the turmoil of gas and magnetic fields in its vicinity. Back in those days, they only knew that the heart of our galaxy was strangely alive with radio noise, hinting at a massive unseen object stirring in the darkness. Radio waves also unveiled phenomena that astronomers had never imagined. In July 1967, a graduate student in England named Jocelyn Bell was monitoring data from a new radio array. Miles of cables and antennae spread across the Cambridge countryside. Amid the sea of graphed signals, she noticed a peculiar set of pulses, sharp blips of radio emission that arrived like clockwork, about once every 1.3 seconds. At first, she and her advisor puzzled over every earthly explanation: interference, satellites, even a misbehaving instrument. When none fit, they half-jokingly dubbed the signals LGM-1 for little green men, wondering if they could possibly be from an alien civilization. It wasn't aliens. Bell had, in fact, discovered something perhaps even more wondrous: a pulsar. In reality, this was the rapidly spinning corpse of a massive star, a neutron star no larger than a city, left behind after a supernova explosion. This tiny object was spinning and flashing beams of radio waves like a cosmic lighthouse. Each time its beam swept past Earth, we detected a pulse. The realization was electrifying. Here was a completely new kind of celestial object. A star had died and collapsed into an ultra-dense ball of neutrons, and yet it lived on, spinning and sending out regular radio heartbeats into space. Jocelyn Bell's discovery was a revelation, proof that the deaths of massive stars could leave behind these city-sized, spinning remnants broadcasting their existence across the cosmos. Around the same time, radio surveys revealed other tantalizing mysteries. At Cambridge University, astronomers compiling catalogues of radio sources found several that defied easy explanation. One source, whimsically named 3C273 in a catalogue, corresponded to a very faint point of light in visible images, like a star, but not exactly. In 1963, using a telescope and a clever trick of observing a lunar eclipse of the source, astronomers identified this faint object's spectrum and were astonished to find it was redshifted to an extreme degree. In simpler terms, it was incredibly far away, billions of light years from Earth, far outside our galaxy. Yet it was emitting tremendous amounts of energy. It turned out to be the first known quasar, short for quasi-stellar radio source. It was a brilliantly luminous core of a young galaxy, powered by a supermassive black hole devouring matter at its center. This single object was so bright that it outshone an entire galaxy of billions of stars, but its light was concentrated in a tiny region. The discovery of quasars forced astronomers to reckon with the extraordinary power of black holes and the vast scale of the universe. A quasar could radiate as much energy as hundreds of normal galaxies combined, all from a volume no larger than our solar system. It was as if a distant beacon had suddenly pierced the cosmic dark, revealing a truth previously unimagined, that the hearts of some galaxies are engines of unbelievable fury. Quasars and pulsars, two utterly different phenomena, had something in common. They were invisible to traditional optical telescopes, or nearly so. Without radio astronomy, we might never have known they existed. But radio waves brought their existence to light, transforming our understanding of what the universe contains. By the end of the 1960s, the once quiet radio spectrum had given voice to an array of cosmic marvels: the whisper of cold hydrogen mapping out our galaxy, the rhythmic heartbeat of pulsars, and the distant cry of quasars powered by voracious black holes. Each was a revelation that the cosmos was richer and more complex than our eyes alone could perceive. Each success in tuning in to these invisible frequencies brought humanity deeper into the cosmic conversation. By the mid-1960s, the airwaves were alive with revelations. Yet the greatest cosmic signal of all was still awaiting discovery. A signal not from stars or galaxies, but from the universe's own birth. In 1964, high above New Jersey, two young scientists stumbled onto a persistent noise in a giant horn-shaped antenna. This faint, steady hiss seemed to come from every part of the sky, day and night, without fail. It was weak, but unrelenting, an ever-present murmur that no amount of troubleshooting could eliminate. Little did they know, they had detected the oldest broadcast in the universe, the afterglow of the Big Bang. Arno Penzias and Robert Wilson, radio astronomers at Bell Labs, were testing a 20-foot horn antenna originally built for satellite communications. They aimed it at empty sky and heard an annoying hum in their receivers. At first, they assumed there must be a mundane source. Could it be urban interference? They checked. Could it be a malfunction in the electronics? They double-checked every circuit. The noise persisted. In desperation, they even climbed inside the antenna and shooed away a couple of pigeons roosting there. The birds had left the antenna's interior encrusted with droppings, a white dielectric material, as Penzias dryly described it. Cleaning it out and evicting the pigeons made no difference. The mysterious hiss remained. No matter where they pointed the antenna, no matter the time of day or season, the soft noise was always there. At a loss, Penzias and Wilson reached out to colleagues at nearby Princeton University. Unbeknownst to them, a team at Princeton, led by physicist Robert Dicke, had been actively searching for that very signal. Years earlier, in the 1940s, scientists Ralph Alpher, George Gamow, and Robert Herman had predicted that if the universe began in a hot Big Bang, it should be filled with a faint afterglow, light from that fiery beginning, stretched to lower energy over billions of years. By the 1960s, Dicke and his collaborators were designing an experiment to detect this cosmic background radiation. When Penzias called up to discuss the stubborn noise in the Bell Labs antenna, Dicke immediately understood what it was. Legend has it that he hung up the phone and turned to his team, saying, "Boys, we've been scooped." Sure enough, Penzias and Wilson had unwittingly discovered the cosmic microwave background, often abbreviated as CMB, the faint glow of the universe's creation. This was light emitted when the universe was in its infancy, now cooled and stretched into the microwave part of the spectrum. The two young radio astronomers published their findings in 1965, and as the significance sank in, the scientific world was astounded. Here was tangible evidence that the universe began in a hot, dense state. The CMB was quickly recognized as a pillar of the Big Bang theory, and Penzias and Wilson would earn Nobel Prizes for their discovery. What exactly is the cosmic microwave background? To picture it, we must journey back nearly 14 billion years to when the universe was a newborn. In those first hundreds of thousands of years after the Big Bang, the universe was a seething cauldron of plasma, matter and light mixed in an opaque fog. Space itself glowed like the interior of a star, a brilliant, hot radiance, because matter was so hot that atoms couldn't hold together. Electrons and protons were flying free, constantly scattering photons. The universe was, in a sense, a brilliant, white-hot glow, but trapped. Light could not travel far without bumping into a particle, so everything was obscured within a bright fog. As the universe expanded, it cooled. After about 380,000 years, it had cooled enough to roughly 3,000 degrees Celsius for electrons and protons to combine into hydrogen atoms. This phase is poetically called recombination, though it was the first time such atoms had ever formed. Suddenly, space went from opaque to transparent. The fog lifted. Photons that had been locked in constant scattering were free to stream away in all directions. The universe's brilliant light was released to travel through space. Over billions of years, that primordial light has been stretched by the expansion of the universe. Once as energetic as the surface of a star, it's now a cold glow, its wavelength lengthened into the microwave part of the spectrum. Today, the cosmic microwave background is extremely faint and chill, only about 2.7 degrees above absolute zero, literally just a few degrees above the coldest temperature possible. It is, effectively, microwave heat coming from all directions, the afterglow of creation filling the cosmos. In fact, if you ever tuned an old-fashioned television to a blank channel and watched the static dance on the screen, a small fraction of that static was caused by the cosmic microwave background. A bit of the snow on those old TV screens was the Big Bang's afterglow, whispering into your living room from the beginning of time. When it was first detected, the CMB appeared astonishingly uniform. It seemed to have almost the same temperature in every direction, smoothed to better than a few parts in 10,000. It was as if the sky were painted with an almost perfectly even brush of primordial light. This observed uniformity was both a triumph and a puzzle. It strongly supported the Big Bang theory. The steady-state theory, which posited no such background, had no answer for this hum. And it suggested that the early universe was remarkably homogeneous. But how could opposite ends of the universe, areas far too distant from each other to have ever exchanged heat or light, share exactly the same temperature? This conundrum, known as the horizon problem, would later inspire bold new ideas like cosmic inflation, the concept that in a fraction of a second after the Big Bang, the universe expanded exponentially, so that regions now far apart were once in close contact. Inflation could explain how the temperature evened out so uncannily. At the time of the CMB's discovery, such theoretical fixes were still brewing, yet scientists already understood that the smoothness of the CMB held profound implications. Still, cosmologists knew this even glow could not be perfectly featureless. According to theory, there must have been tiny irregularities in density in the early universe, slight lumps and bumps in that primordial soup. Over cosmic time, gravity would amplify those slight overdensities into galaxies and clusters of galaxies. If the early universe had been completely smooth, there would be no seeds for structure, and we wouldn't exist. So researchers believed that the CMB, if measured with enough sensitivity, would show subtle variations, tiny warmer and cooler spots, reflecting those seeds of structure. Detecting those minuscule fluctuations would be a major challenge, like finding faint freckles on an otherwise smooth surface. But it was essential. It was the key to understanding how the universe grew up from a hot, uniform baby to the richly structured cosmos of stars and galaxies we see today. Decades of experimental effort followed the CMB discovery. In laboratories and observatories around the world, teams built ever more sensitive radiometers and bolometers, climbed mountains, lofted instruments on high-altitude balloons, and eventually launched satellites, all to measure the precise texture of this background light. The task was daunting. They were looking for temperature differences of only millionths of a degree. The signal had to be disentangled from the faint whisper of the Milky Way's own microwave emissions, and from the instrument's noise. For a long time, the CMB looked perfectly uniform within the limits of measurement. But patience and technology paid off. In 1992, nearly 3 decades after its discovery, NASA announced a breakthrough. Data from the COBE satellite, Cosmic Background Explorer, which had been launched in 1989, revealed the first tiny variations in the microwave background. COBE's sensitive instruments mapped the sky and found that the CMB is not absolutely smooth. It has faint hot and cold spots on the order of 1 part in 100,000 above or below the average temperature. a false colour map unveiled a delicate speckled pattern across the sky, a cosmic tapestry of subtle blotches, slightly warmer here, slightly cooler there. The differences were vanishingly small, mere tens of millionths of a degree, but they were real. When these results appeared, there was a moment of awe among cosmologists. The project's lead scientist, George Smoot, famously said, "If you're religious, it's like seeing the face of God." What he meant was that this was a direct imprint of creation, the fingerprints of the primeval universe visible at last. Those modest fluctuations were exactly what theory had predicted, the seeds from which galaxies would grow, finally in our grasp to observe. With this map, cosmology moved from speculation to precision. The COBE findings confirmed the basic story of cosmic evolution and gave credence to the idea of inflation, which could naturally produce just such a pattern of initial irregularities. Two of COBE's chief scientists, George Smoot and John Mather, would later receive the Nobel Prize for this achievement. After COBE's success, the quest to map the CMB in greater detail accelerated. In the 2000s, a satellite called WMAP, Wilkinson Microwave Anisotropy Probe, measured the CMB with far higher resolution and sensitivity, producing a beautifully detailed all-sky portrait of the infant universe. By the 2010s, the Planck satellite, a European-led mission, refined that portrait even further. These maps showed the CMB's mottled pattern with unprecedented clarity. It was as if we had taken a slightly blurry baby photo of the universe and progressively sharpened it to see fine details of its complexion. Tiny variations on scales of 1/10 of a degree became clear. Cosmologists could read this pattern like a code, extracting the universe's age, about 13.8 billion years, its composition, only about 5% normal matter, the rest being dark matter and dark energy, and even clues to the geometry of space, remarkably flat on large scales. The data from WMAP and Planck fit the Big Bang model with stunning precision. Yet, intriguingly, amidst the random speckles of hot and cold, a few oddities appeared, hints that perhaps something more was at play than pure chance. These are called anomalies in the CMB. Most of them are subtle statistical quirks, still debated among experts as to whether they mean anything physical or are just flukes of random patterns. But one anomaly stood out dramatically and captured public imagination: the cosmic cold spot. In one region of the southern sky, roughly in the direction of the constellation Eridanus, the microwave background has a patch that is significantly cooler than average, and not just by a tiny amount, and not just in 1 pixel, but over a relatively large area. The cold spot spans about 5 to 10 degrees of the sky. Compare that to the moon's half-degree size. This spot is huge by celestial standards. It is about 70 microkelvins, millionths of a Kelvin, colder than the surrounding regions. At first glance, a difference of 70 microkelvins sounds infinitesimal. But in the context of CMB fluctuations, it's unusually large. Most spots in the CMB are on the order of 20-30 microkelvins, in contrast, and they occur on smaller scales. This one dwarfed them, a big, cool region that just shouldn't be that pronounced. The cold spot was first noticed in the WMAP data in the early 2000s. When the map's data were analysed, some scientists double-checked it to ensure it wasn't an error or artifact of processing. But with each new data release, the spot persisted. Many initially wondered if it could be a fluke, perhaps just a random clustering of slightly colder spots that happened by chance. After all, in any random pattern, you can find something that looks unusual if you search long enough. It was as if you had flipped a coin thousands of times and somewhere in the sequence found an unusually long run of tails. Not impossible, but highly improbable. As more data came in, the cold spot remained, and it became increasingly clear that this wasn't a mere statistical hiccup, easy to brush aside. Planck's observations in 2013 confirmed the cold spot's existence with high confidence. Statistically, given our standard cosmological model, which assumes the CMB fluctuations are random and Gaussian, the chance of having such a large, deep cold region is very small, on the order of 1 or a few percent. In other words, it's an outlier, a lucky or unlucky roll of the cosmic dice, if indeed it is just luck. Its unlikelihood prompted scientists to take it seriously and investigate possible causes. What could make such a sizable patch of the CMB cooler than its surroundings? One straightforward idea was just that: cosmic luck. After all, with billions of patches across the sky, some rare fluctuation might occur somewhere. Perhaps we simply won the lottery of randomness, and our universe's initial conditions happen to include one especially large cold deviation. In the multiverse of all possible outcomes, even low probability events can happen. But to many scientists, that explanation felt unsatisfying. It would mean our observable universe is just a slightly weird draw from the cosmic lottery, with no deeper significance. So researchers began looking for physical causes. They asked, could something relatively nearer to us, in the line of sight between here and that distant surface of last scattering, be responsible for the cold spot? When we look at the CMB, we are effectively looking through the entire universe, all the way back in time. Any structure between here and there could, in principle, influence the CMB photons on their journey. Around 2007, astronomers conducting galaxy surveys in the direction of the cold spot found hints that that region of space might contain far fewer galaxies than average. In other words, a huge cosmic void. Follow-up observations suggested the presence of a vast supervoid, perhaps hundreds of millions of light-years across, relatively closer to us, on the order of 3 billion light-years away. This supervoid, an enormous volume of space with much lower density of matter and galaxies, could affect the energy of CMB photons passing through it via the integrated Sachs-Wolf effect. Here's the idea. As CMB photons enter a void, they gain a little energy, falling into the void's gravitational well, which is shallow because the void lacks mass. As they exit, the void's gravity pulls on them, trying to sap that energy. In a universe that's expanding, with dark energy pushing expansion to accelerate, the void effectively stretches while the photon is crossing it, so the photon doesn't fully regain all the energy it gained going in. The result is that the photon emerges slightly less energetic, a bit cooler, than it would have been otherwise. If you have an especially large and deep void, this effect could dim the CMB's temperature across that patch of sky. Some studies indeed argued that this Eridanus supervoid might account for a significant portion of the cold spot's temperature drop. The idea was enticing. Perhaps the cold spot was not a primordial anomaly at all, but rather a shadow cast on the CMB by this enormous emptiness much closer to us. In 2015, a team led by astronomer Istvan Sapudi reported finding evidence of a supervoid aligned with the cold spot, adding weight to this hypothesis. However, even the void explanation has challenges. Estimates suggested that the void, while big, might not be big enough or empty enough to cause the full magnitude of the cold spot. It could be a piece of the puzzle, but perhaps not the whole story. So, the door remained open for more exotic ideas. One far-out possibility was that the cold spot is a bruise from another universe. In some speculative inflationary models, our universe might be just one bubble in an infinite foamy multiverse. Once in a while, bubbles could collide. If another universe's bubble wall hit ours in the deep past, it might have left a round imprint on the CMB, a disturbance in the temperature pattern. The cold spot, with its roughly circular, distinct appearance, tantalized some as a potential sign of such an event. If true, and to be clear, this is a minority and highly speculative view, it would mean the cold spot is literally a cosmic scar from a collision with another universe. The excitement of that idea captured the public's imagination. Evidence of a multiverse, perhaps. Though most scientists view it skeptically, as extraordinary claims require extraordinary evidence. Another proposal invoked exotic physics in our own universe. Maybe a so-called cosmic texture caused the cold spot. Textures are a kind of topological defect that could form during phase transitions in the early universe, analogous to cracks that form when water freezes into ice. If a texture were present, as it unwound or decayed, it could leave a cold and hot imprint on the CMB. Some models of particle physics predict such things, though none are confirmed. The cold spot spurred papers analyzing whether a texture could fit the data. Thus far, no single explanation has been universally accepted. It may turn out that the cold spot is a combination of factors, part supervoid effect, part statistical fluke. As data improved, some analyses have slightly downplayed the cold spot's improbability. But it remains, at the very least, an intriguing feature that prompts us to question our assumptions. It reminds us that even with a precision cosmology model that fits so much, nature can still surprise us with something we didn't expect. One thing is certain. Whether the cold spot is just a curious but ultimately mundane feature, or a key to new physics, it has stimulated plenty of discussion about the early universe and large-scale structure. In scientific exploration, anomalies are precious. They prod us to test the limits of our theories and sometimes lead to breakthroughs. The enduring enigma of the cold spot is a gentle whisper hinting that we might not yet have all the answers about the cosmos's earliest moments. While the cosmic microwave background speaks of the universe's infancy in a gentle, all-pervading whisper, the universe has other stories to tell, stories of high drama and violence that unfold on a later stage of cosmic time. To hear those tales, we must turn our attention to wavelengths of light far shorter and more energetic than microwaves. Now, our exploration of the invisible cosmos leads us beyond the thermal afterglow of creation and into the realm of X-rays, a part of the spectrum where the universe reveals some of its most furious and fiery events. And to detect this high-energy light, we would have to venture beyond Earth's protective atmosphere, leaving behind the comfort of ground-based observatories for rockets and satellites. For human eyes, X-rays are entirely invisible, and thankfully so, for X-rays are a form of energetic radiation that can be harmful to living cells. Fortunately for us, Earth's atmosphere acts like a shield, absorbing X-rays and even higher energy gamma rays from space before they reach the ground. This is a boon for life, protecting us from dangerous cosmic rays. But for astronomers, that protective blanket posed a problem. It meant that the X-ray sky was completely hidden. For millions of years, no creature on Earth ever saw or felt a cosmic X-ray. It wasn't until the mid-20th century, with the advent of rockets and spaceflight, that scientists found a way to slip above the atmosphere, if only briefly, and open new eyes on the X-ray universe. By the 1960s, researchers realized that to witness the universe's most energetic phenomena, they would have to lift their instruments into the high atmosphere or beyond, even if only for a few minutes at a time. Only by venturing above our planet's air could we begin to glimpse the cosmos in X-ray light. In the late 1940s and 50s, a few experiments using captured German V-2 rockets were flown to high altitudes to detect X-rays from the sun. Those early attempts confirmed that the sun does emit X-rays, especially during solar flares, but they also suggested the sun wasn't a terribly strong X-ray source most of the time. Some scientists doubted that anything beyond the sun, say other stars, would be bright enough in X-rays to detect across space. After all, if our relatively nearby sun barely registered, what hope was there for distant cosmic objects? For a while, this skepticism reigned. Yet, a small cadre of pioneers continued to push the idea of X-ray astronomy. On a hot, dry morning in the New Mexico desert in June 1962, a team of scientists led by Riccardo Giacconi prepared a daring experiment that would forever change our view of the high-energy universe. They set up a sounding rocket, a slender Aerobee 150 rocket, fitted with a crude X-ray detector, essentially Geiger counters and scintillators. The goal was modest. They hoped to detect X-rays from the moon, indirectly, by seeing if the moon shone in X-rays due to reflecting the sun's X-rays. It sounded like a long shot, but they had to try something. Just before midnight on June 18, 1962, the rocket roared to life and streaked upward. Within minutes, it passed above 99% of Earth's atmosphere, giving the detector a few hundred seconds of near-space exposure to the X-ray sky. High above the desert, as the rocket's payload briefly hung in space, the instruments began registering far more counts than expected. The Geiger counters buzzed to life with a flurry of clicks. By the time the rocket parachuted back to Earth, the scientists had gathered data that hinted at a monumental discovery. When Giacconi and his team analyzed the results, they found not just the faint whisper of a potential lunar reflection, but the booming signal of a bright X-ray source far beyond the solar system. It appeared to come from the direction of the constellation Scorpius. They named this enigmatic beacon Scorpius X1, meaning the first X-ray source found in Scorpius. This was the birth of X-ray astronomy. Galileo, over 350 years earlier, had pointed a telescope to the sky and discovered moons around Jupiter, objects invisible to the naked eye, which revolutionized our understanding of the cosmos. Now, in 1962, humanity had, in effect, done something analogous, but in a new spectrum. We had turned an X-ray detector to the sky and found the unimaginable. The notion that there were objects in space emitting X-rays intense enough to be detected was proven true, defying the doubts of earlier experts. In one 5-minute rocket flight, the team uncovered a whole new universe of high-energy phenomena. Scorpius X1 turned out to be a true powerhouse. Further study revealed that SCO X1 is a faint blue star in visible light, thousands of light years away, utterly unremarkable to an optical telescope. But in X-rays, it outshines virtually everything else in the sky, second only to the sun. What was it? Over time, researchers determined that Scorpius X1 is a binary system, a small, dense neutron star pulling matter off a normal companion star. As gas from the companion spirals onto the neutron star's surface, it is superheated to millions of degrees, releasing torrents of X-rays. SCO X1 pumps out X-ray energy at a rate tens of thousands of times greater than the sun's total energy output across all wavelengths. Yet all of that ferocity was invisible until we tuned in with X-ray ears. The discovery of such a source was astonishing. It hammered home the lesson that the universe can be wildly different when viewed in different kinds of light. Scorpius X1 in visible light was a nondescript pinpoint. In X-rays, it was a beacon blazing with the energy of a whole galaxy's worth of stars. Nature was conducting high-energy fireworks in secret, and at last we had caught a glimpse. Once that door was opened, the floodgates of discovery followed. Throughout the 1960s, scientists launched more sounding rockets, and even balloons lofted to high altitudes, each probing the X-ray sky a bit further. They began finding additional X-ray sources. One bright X-ray emitter was located in the remnants of an exploded star, the Crab Nebula, which is the debris of a supernova observed by humans in 1054 AD. The Crab Nebula pulsar, a rapidly spinning neutron star at its center, accelerates particles to tremendous speeds, causing high-energy radiation including X-rays. So the Crab, already famous as a beautiful glowing cloud in optical light, was revealed to be a strong X-ray source as well, aglow with the shock waves of its ancient explosion. Another surprise came from the constellation Cygnus. A strong X-ray source dubbed Cygnus X1 was discovered in the late 1960s. By the early 1970s, astronomers identified its optical counterpart, a bright, massive star that seemed to be orbiting an unseen partner. The X-rays from Cygnus X1 varied rapidly, suggesting a very small, extremely energetic source. The pieces clicked together. Cygnus X1 was likely a black hole, a stellar mass black hole devouring gas from its stellar companion, heating the gas to X-ray emitting temperatures as it fell into the gravitational abyss. This became one of the first strong black hole candidates ever identified. Even the famously skeptical physicist Stephen Hawking, who had bet against its being a black hole, eventually conceded and paid off the bet. Here again, X-rays had unveiled something invisible in every sense. You can't see a black hole directly, but you can see the furious radiation from matter as it swirls in, just before the final plunge. X-ray telescopes had effectively found a cosmic dragon by spotting its fiery breath. By the end of the 1960s, dozens of X-ray sources had been detected. Clearly, the X-ray sky was rich. But to truly map and study it, longer observations from space were needed, more than a few minutes from a rocket or hours from a balloon. In 1970, the era of X-ray satellites began with the launch of a NASA satellite named Uhuru, which means freedom in Swahili. It was launched from Kenya on the anniversary of Kenyan independence. Uhuru was the first orbiting X-ray observatory, and during its 2-year mission, it catalogued several hundred X-ray sources across the sky. For the first time, astronomers had a full sky inventory of the brightest X-ray objects. Many turned out to be binary star systems with neutron stars or black holes, like Scorpius X1 and Cygnus X1. Others were supernova remnants, like the Crab. Some were active galaxies and quasars, incredibly, shining in X-rays from their central engines. Uhuru firmly established X-ray astronomy as a new and thriving branch of astronomy. As technology advanced, more sophisticated X-ray satellites followed. In 1978, NASA's Einstein Observatory, named after Albert Einstein, carried the first imaging X-ray telescope into orbit. Unlike earlier detectors that could only count photons, Einstein had mirrors designed to focus X-rays by using tightly nested shallow-angled reflectors, since X-rays would penetrate a normal mirror. For the first time, X-ray sources could be seen as images rather than just point detections with crude positions. The universe in X-rays came into focus. Einstein Observatory captured the glowing blast waves of supernova remnants, the fiery halos of galaxies, and the hot gas-pervading clusters of galaxies. It takes a lot of energy to make X-rays, and that's what makes X-ray astronomy so exciting. It highlights the most violent and extreme phenomena in the cosmos. With the Einstein Observatory and later missions like Germany's Rosat in the 1990s, and most spectacularly, NASA's Chandra X-ray Observatory, launched in 1999, and ESA's XMM Newton, also 1999, we gained exquisitely sensitive eyes on the X-ray sky. To build these X-ray eyes, engineers had to solve a tricky problem. X-rays would normally either pass through or be absorbed by a regular telescope mirror. The solution was to use mirrors shaped like barrels or cones, so that X-rays would just graze the surfaces at shallow angles and be deflected to a focus. The result, in Chandra's case, was sub-arc-second resolution, incredibly sharp X-ray vision. With these observatories, we've captured breathtaking vistas of high-energy cosmos that were once completely hidden. Through X-ray eyes, we have witnessed whole new chapters of cosmic evolution. Entire clusters of galaxies, the largest gravitational structures in the universe, were found to be filled with turbulent, multi-million-degree gas that shines brightly in X-rays. In visible light, a galaxy cluster is a clump of galaxies on a dark background. But in X-ray light, that dark space between galaxies is revealed to be full of hot plasma, often more massive than all the galaxy's stars combined. For example, the Perseus cluster shows up in X-rays as a huge diffuse glow, with curious ripples propagating through it, which turned out to be actual sound waves on a tremendously low pitch, caused by repeated outbursts from the central galaxy's supermassive black hole. Observing clusters in X-rays taught us that they contain vast reservoirs of matter, and that even more unseen dark matter must lurk to hold that hot gas in the cluster's deep gravitational well. It is an X-ray view that unveiled phenomena like the bullet cluster, where two clusters have collided. The X-ray image displays gas stripped out in the impact, separable from the galaxies, offering direct evidence for dark matter's existence as distinct mass. We have also peered into the hearts of galaxies using X-rays. The center of our Milky Way, for instance, is shrouded by dust in optical light. But X-ray observations can penetrate that dust. Chandra has shown the Milky Way's core to be bustling with high-energy activity. There are neutron stars and black holes accreting matter, supernova remnants, and an occasional flare from the supermassive black hole Sagittarius A itself, which normally is quiet but sometimes spits out X-ray flashes when it guzzles a clump of gas. In distant active galaxies, called blazars, where a jet from the galaxy's central black hole points towards Earth, X-ray telescopes catch intense radiation from particles accelerated to nearly light speed in those jets. Another achievement of X-ray astronomy was resolving the long-standing mystery of the cosmic X-ray background. When Giacconi's team flew that first rocket in 1962, along with SCO-X-1, they noticed a faint, diffuse X-ray glow across the sky. For a while, scientists weren't sure what it was. Perhaps hot gas spread throughout intergalactic space, or innumerable unresolved sources. In the late 1990s and early 2000s, deep observations with Chandra and XMM Newton were finally able to resolve the X-ray background into discrete sources. By pointing at a seemingly empty patch of sky for days, these telescopes detected hundreds of faint X-ray sources. The majority turned out to be distant active galactic nuclei, basically quasars and galaxy centers with accreting black holes, whose combined glow creates the illusion of a diffuse background. What had once been thought of as a uniform X-ray hiss turned out to be the chorus of millions of high-energy engines at the hearts of galaxies, each too faint to notice alone until we integrated enough exposure. It's an example of how the universe, even in its blankest corners, teems with activity when you have sensitive enough instruments. X-ray observations have transformed our understanding of the cosmos. We have seen matter torn apart. For instance, in the constellation of Pegasus, Chandra observed a star being shredded by a black hole in a galaxy millions of light years away, a flare of X-rays marking the star's death. We have watched galaxies collide, their gas crashing together to produce enormous X-ray fireworks, revealing shock fronts and new heating as they merge. We have found magnetars, ultramagnetized neutron stars, which occasionally unleash tremendous blasts of X-rays and gamma rays when their magnetic fields fracture. Starquakes on objects the size of a city, but with magnetic fields trillions of times Earth's. We've even detected X-ray flashes from distant gamma-ray bursts after the initial gamma flash fades, helping us pinpoint their locations. In one case, astronomers using X-ray and other telescopes observed something momentous. Two neutron stars merging in a galaxy. This event, detected in 2017, first announced itself via gravitational waves, a ripple in spacetime that set off the LIGO and Virgo detectors on Earth, and seconds later, a burst of gamma rays detected by satellite. Chandra was on the scene within weeks to observe the X-ray afterglow of this merger. This was a historic first, a multi-messenger astronomy moment where gravitational waves and electromagnetic waves, gamma ray, X-ray, optical, etc., all told different parts of the same story. It confirmed that short gamma-ray bursts, one class of the GRBs we'll soon discuss, come from neutron-star collisions, and it even gave insight into the formation of heavy elements like gold in the explosive aftermath. Yet, even X-rays are not the final word in high-energy cosmic storytelling. There is a form of light even more energetic, more penetrating, capable of probing the universe's most cataclysmic events. These are gamma rays, the shortest wavelength, highest frequency, electromagnetic waves. If X-rays show us exploding stars and hot gas, gamma rays reveal nature's biggest explosions and most extreme phenomena: nuclear reactions, matter-antimatter annihilations, and ultrafast particle acceleration. To open our ears to the gamma-ray chorus of the cosmos, we had to push our technology to its limits, and once again, venture into space, since Earth's atmosphere zealously blocks gamma rays, which, given their dangerous nature, is a very good thing for us on the ground. The story of cosmic gamma rays reads like a Cold War thriller. In the late 1960s, at the height of Cold War tensions, the United States deployed a series of satellites called Vela to monitor compliance with the Nuclear Test Ban Treaty. These satellites orbited Earth, carrying detectors meant to catch the distinctive gamma-ray flash of clandestine nuclear explosions in the atmosphere or in space. On July 2, 1967, one of these Vela satellites indeed detected a burst of gamma radiation. The signal set off alarms. It looked somewhat like what a nuclear bomb's gamma-ray pulse might look like. But it soon became apparent that the flash did not come from Earth, or even near Earth. It came from somewhere in deep space. Over the next few years, more mysterious gamma bursts were recorded by the Vela satellites. Because of their military implications, these findings were initially classified. But once it was clear they were not of terrestrial origin, and thus not Soviet nuclear tests, the data were declassified. In 1973, a team of Los Alamos scientists published the discovery of gamma-ray bursts, GRBs, revealing that these short, intense flashes of gamma rays were coming from random directions in the sky. Each burst lasted only seconds, maybe minutes at most, then disappeared. They were unpredictable. There was no telling when or where the next one would occur, and they were astonishingly powerful. Even from whatever great distance they originated, they produced a significant spike in the satellite detectors. To generate that kind of burst of gamma rays, the events had to be immensely energetic. These gamma-ray bursts instantly became one of the biggest mysteries in astrophysics. For a while, theories proliferated wildly. Some hypothesized they might be flare-ups of neutron stars within our own Milky Way, perhaps some exotic kind of starquake or magnetospheric event. Others suggested even more exotic ideas like annihilating black holes or collisions of matter and antimatter clouds. The truth was, nobody knew, because pinpointing their location was so difficult. The gamma detectors of the era could give only rough positions, and no counterparts were seen in optical or other wavelengths at those positions. After all, by the time you swung a telescope to look, the GRB was long gone. It was like hearing distant, sporadic gunshots in the dark and not knowing who fired or from where. Throughout the 1970s and 80s, dedicated gamma-ray satellites detected additional bursts and also mapped the gamma-ray sky in general. They discovered that aside from bursts, the sky had a diffuse gamma glow and a few steady sources. But GRBs remained the tantalizing mystery. One big question: were they nearby or cosmologically distant? If they were in our galaxy, their energy output could be somewhat modest. If they were in distant galaxies, their energy would be mind-bogglingly enormous. In a few seconds, they'd be releasing more energy than an entire galaxy does in months or years. For a long time, arguments bounced back and forth. The distribution of bursts in the sky observed by the 1991 launched Compton Gamma Ray Observatory was uniform. They were coming from all over, not concentrated in the Milky Way's plane. That hinted they might be extragalactic. Still, absence of evidence isn't evidence of absence, as the saying goes. Maybe they were in a huge halo around our galaxy or something. The breakthrough finally came in 1997. A satellite called Beppo-Sachs had the ability to quickly point an X-ray telescope at a GRB's location within minutes of a burst detection. In February 1997, a gamma-ray burst went off, and Beppo-Sachs slewed to catch its fading afterglow in X-rays. Crucially, they also found a faint fading source in visible light, the first ever optical afterglow of a GRB, pinpointing its location precisely. Within weeks, astronomers identified a distant host galaxy at that position. When they measured its redshift, it was clear. The GRB had occurred billions of light years away. That burst, so bright in gamma rays that it was detected by satellites here, had originated across an immense span of the universe. The energy it must have released was almost unthinkable. Piece by piece, the GRB puzzle came together. Observations in subsequent years revealed that there are, broadly, two types of gamma-ray bursts. Long-duration bursts, lasting more than 2 seconds, often tens of seconds, and short-duration bursts, lasting less than 2 seconds. The long ones were found to coincide in time and location with brilliant, peculiar supernova explosions, the death throes of extremely massive stars. It turns out that when a star perhaps 30 or 50 times the sun's mass collapses at the end of its life, it can produce a special kind of supernova, sometimes called a hypernova, with jets of material screaming out of the poles at nearly light speed. If Earth lies in the path of one of those jets, we see a gamma-ray burst. The short bursts, on the other hand, were eventually traced to mergers of neutron stars, an idea dramatically confirmed in 2017 when gravitational wave detectors and gamma-ray telescopes caught the very same event. Two neutron stars colliding, producing gravitational waves and a short GRB. For gamma-ray bursts, saying they are powerful feels like an understatement. For those few seconds of a burst, the power output can exceed that of all the stars in the observable universe combined. Thankfully, they are far away, usually billions of light years, so we only detect the tail end of their fury. Were one to occur in our own galaxy, within a few thousand light years pointing at us, it could potentially damage our ozone layer, or worse. But space is huge, and such events are rare and directional, so the odds are low. Gamma-ray astronomy isn't only about bursts, however. Aside from GRBs, there are steady or variable gamma sources. Pulsars, for instance, which we met earlier as radio pulsars, often emit gamma rays as well. The Vela pulsar, in the Vela supernova remnant, is a strong gamma pulsar. It flashes gamma rays at the same rhythm as its radio pulses. Magnetars, a type of neutron star with ultra-strong magnetic fields, can emit sudden, giant gamma-ray flares. In 2004, a magnetar in our galaxy, called SGR 1806-20, released a burst so intense that it briefly ionized Earth's upper atmosphere from 50,000 light-years away. It was one of the brightest extrasolar gamma events detected in modern times. Our own sun, benign as it is in the life-sustaining sense, occasionally produces gamma rays during solar flares. These solar gamma rays are far weaker than cosmic ones, but were also first detected by early satellites. They result from high-energy processes when the sun's magnetic fields snap and accelerate particles. Distant galaxies with accreting supermassive black holes, active galactic nuclei, can shine brilliantly in gamma rays too. In particular, blazars, active galaxies with jets aimed at us, are prominent gamma ray sources. The combined glow of innumerable distant AGN also creates a sort of gamma ray background across the sky, analogous to the X-ray background, but even higher energy. Modern missions like NASA's Fermi Gamma Ray Space Telescope, launched 2008, have catalogued thousands of gamma ray sources, including pulsars, supernova remnants, star-forming galaxies, and active galactic nuclei. Detecting gamma rays requires ingenious techniques. In space, telescopes like Fermi's LAT, Large Area Telescope, use layers of detectors where incoming gamma photons convert into electron-positron pairs and then leave tracks. Essentially, they are particle detectors doubling as telescopes, since gamma rays can't be focused by normal mirrors. On the ground, we still cannot directly observe cosmic gamma rays. They get absorbed in the atmosphere. But we've found a clever workaround: Cherenkov telescopes. When a high-energy gamma ray strikes the upper atmosphere, it triggers a cascade of secondary particles, a little air shower, that moves faster than the local speed of light in air, producing a faint bluish flash known as Cherenkov radiation. By monitoring the dark sky with large optical reflectors equipped with fast sensors, astronomers can catch those brief blue flashes. From the pattern of light, they infer the energy and origin of the original gamma ray. Facilities like HESS in Namibia, MAGIC in the Canary Islands, and Veritas in Arizona employ this technique. At night, under moonless skies, these telescopes don't look at stars. They watch for ghostly, split-second glimmers of particle cascades. It's a bit like seeing lightning in a distant storm and deducing how powerful the bolt was and where it came from, even though you didn't see the bolt directly. This ground-based gamma-ray astronomy has enabled us to detect the highest energy photons of all in the TeV, tera-electron-volt, range, coming from sources like the Crab Nebula, which is a veritable particle accelerator, courtesy of its pulsar, and extreme active galaxies. We've learned that the universe is peppered with cosmic accelerators that put human particle colliders to shame. By now, we have opened our senses to nearly the full electromagnetic spectrum, from the longest radio waves through microwaves and infrared, the familiar visible band, onward to ultraviolet, X-rays, and gamma rays. Each new band has revealed a different facet of the cosmos, uncovering phenomena we didn't know existed. It's as if we've gradually assembled a grand orchestra, section by section, that had been playing around us all along. The radio section brings deep, resonant notes of star birth and galactic structure. The microwave section carries the ancient echo of the Big Bang. The optical and infrared give melody and harmony to stars and galaxies. The X-rays contribute the dramatic, high-energy riffs of violent transformations. And the gamma rays crash in like cymbal strikes, rare and thunderous, marking the universe's most explosive events. Through these multi-wavelength eyes and ears, we piece together a richer, more complete story of our universe. We see how stars are born in cold clouds, radio and infrared, shine brilliantly, optical, and sometimes die in fantastic explosions, optical, X-ray, gamma. We witness how galaxies form and collide, how black holes lurk at their hearts influencing environments, radio jets, X-ray flares. We hear the faint chorus of the Big Bang's afterglow filling the cosmos, microwaves. We catch the crackle of high-energy particles and the whisper of dark matter's presence through hot gas, X-rays, and gravitational effects. The universe has become a symphony to us, with each wavelength adding an instrument to the score. Yet, even after tuning in to this cosmic symphony in all these forms of light, enigmas remain. The cosmic cold spot is one such enigma, a subtle anomaly from the dawn of time that still puzzles us. We have all this data, all these glorious multi-wavelength observations, and a cosmological model that explains so much. And still, there are questions like, why is that patch of the CMB so cold? What does it mean for our understanding of the universe? To answer that, we must be willing to venture beyond the data we've gathered and into the realm of theory and conjecture. We have to examine bold ideas about the universe's structure, about inflation and multiverses, and test them against what we observe. Perhaps the cold spot will turn out to be a mere statistical fluke combined with a large void, a message that our universe, though extraordinary, is normal after all. Or perhaps it is a signpost leading to new physics, hinting at phenomena we haven't yet fully grasped. Our journey is not over. We've extended our senses to every kind of electromagnetic wave, and even begun to use other messengers like gravitational waves and neutrinos. Each has enriched our understanding, but also uncovered new mysteries. The cosmos, it seems, always has another secret waiting just at the edge of detection, just beyond the current frontier of knowledge. Now, having explored the cosmos across the spectrum of invisible waves, from the gentle hiss of the CMB to the fierce blast of gamma-ray bursts, we turn our attention back to the cosmic cold spot, that curious blemish on the baby picture of the universe. In the next part of our journey, we will delve into what this anomaly could signify. We will sift through the theoretical possibilities, be it a supervoid in our cosmic neighborhood, an imprint of exotic new physics, or even the ghostly signature of another universe brushing against our own. We will see how scientists use every tool, from simulations of cosmic inflation to surveys of galaxies, to test these ideas. The quest is not just to explain one cold patch, but to ensure we truly understand the principles that governed the universe's birth. Our exploration continues, guided by both data and imagination. The sky, in all its wavelengths, has stories left to tell. And as we chase those stories, from the large-scale mysteries like the cold spot to the tiniest vibrations of spacetime, we carry with us the wonder that every new discovery brings. The universe is vast and deep, and much of it remains shadowed in questions. But step by step, wave by wave, we illuminate the darkness. The invisible becomes visible, the silent becomes audible, and the mysterious inches closer to comprehensible. It is a journey that links our clever curiosity with the cosmos itself, an ongoing dialogue between humanity and the stars, written in the language of light. The cosmic symphony of invisible messengers draws our attention not only to distant corners of space, but also to the depths of time. Each whisper from a cosmic ray, each fleeting burst of neutrinos, and each faint ripple of a gravitational wave tells a part of an ancient story. Collectively, they beckon us further back, toward the universe's earliest moments. We follow their lead, journeying to an era when the cosmos was newborn, wrapped in a hot, glowing fog. In that infant cosmos, long before stars or galaxies, subtle imprints were pressed into the fabric of space itself. These imprints, still present after billions of years, hold clues to cosmic events that shaped everything to come. In the darkness of modern space, our eyes cannot see these ancient marks directly. They reside in a form of light beyond the visible spectrum, a gentle afterglow that bathes the entire sky. This is the cosmic microwave background, the faint echo of the Big Bang's brilliance, now cooled and stretched to microwave wavelengths. It surrounds us on all sides, an almost uniform glow only detectable with sensitive instruments. This background light is like a photograph of the universe as a baby, an image taken long before any life existed to witness it. Spread across that image are tiny variations in temperature, slight irregularities that betray places where the young universe was ever so slightly hotter or colder, denser or thinner. Astronomers render this faint background as a map of subtle colours, each hue representing a minuscule difference in temperature from the average. Most of these variations are random speckles, the result of quantum fluctuations blown up by the process of cosmic inflation at the dawn of time. Those tiny fluctuations eventually grew into the galaxies and clusters of galaxies we see around us today. In this way, the mottled pattern on the cosmic microwave background is a blueprint of our universe's large-scale structure. It is a treasure trove of information, a cosmic time capsule carrying messages from when the universe was only a few 100,000 years old. Yet among the gentle, random patchwork of warm and cool spots on this map, one feature stands apart, quietly defying expectations. In a certain patch of sky, far larger and colder than its surroundings, lies a mystery known as the cold spot. While most of the variations in the cosmic background are tiny and statistically unremarkable, the cold spot is different. It covers a region so large and so unusually cold that it caught scientists' attention immediately when the first detailed sky maps were produced. At first glance, it appears as a broad swath of slightly cooler temperature, a faint blue dimple in the cosmic heat map, larger and deeper than any other on the sky. The discovery of the cold spot was met with both excitement and puzzlement. Here was an imprint from the early universe that seemed to whisper of something unexpected. Could it be a statistical fluke, a random chance occurrence in the grand cosmic lottery of fluctuations? Or was it telling us of some special event or structure, either in the early universe or somewhere between those ancient times and our telescopes today? At the time of its detection, no one could say for sure. It became a subject of intense study and debate, a riddle from the dawn of time waiting to be solved. As researchers examined the cold spot more closely, its significance grew harder to dismiss. If the universe were perfectly random in its early fluctuations, the odds of getting such a large, deep, cold region by chance were very small. It was as though the infant universe had left a unique birthmark, one that standard cosmological theories did not readily predict. Some scientists cautioned that even rare events can happen without new physics. After all, given enough area of sky, unlikely things do occasionally occur. Perhaps the cold spot was just a 1 in a million quirk in the cosmic pattern, a statistical outlier with no deeper meaning. But others felt that nature might be hinting at something more profound. To decipher this puzzle, scientists began considering scenarios that could produce such an imprint. The journey of exploration turned speculative and creative. Was there something lurking, unseen, along the line of sight that might have cooled the light from the early universe as it travelled billions of years to reach us? Or did the phenomenon originate at the cosmic dawn itself, an echo of new physics that standard cosmology had yet to account for? Each possibility carried profound implications. With curiosity piqued, researchers looked beyond the usual explanations. They set their sights on the invisible and the exotic, on ideas that stretched the limits of our understanding of the cosmos. In this quest, the cosmic microwave background became more than just a silent image of the past. It became an active playing field for theories. Each subtle anomaly etched in its pattern might be a clue. Perhaps the cold spot was a message from the universe's infancy, left for us to find eons later. If so, what event could have left such an outsized mark? In the smooth fluid of the hot, early universe, what could carve out a region that ended up cooler than its surroundings? It was time to explore answers hidden in the fabric of space and time itself, buried in the realm of the invisible universe beyond ordinary sight. One bold idea was that the cold spot might be the visible imprint of an invisible cosmic relic, a relic not of matter or light, but of a structural twist in the very space that filled the young universe. In other words, some researchers suggested that the cold spot is an ancient cosmic scar left behind by a cosmic texture. In the language of physics, cosmic textures are a type of topological defect, essentially imperfections in the fabric of the young universe. They are akin to knots or twists that form when the universe undergoes rapid phase transitions. Think of how water freezes into ice. As crystal structures form, cracks or bubbles can appear where the freezing isn't perfectly uniform. This is one example of how imperfections can arise naturally during a phase transition. Likewise, as the searing plasma of the early cosmos cooled and transformed, it may have left behind tiny imperfections in the otherwise smooth fabric of space. Cosmic textures represent one possible kind of such imperfection, emerging as the universe's fundamental fields settled into their new states. Not all cosmic imperfections are alike. Theoretical physicists have envisioned other kinds of primordial defects, cosmic strings that stretch like ultra-thin filaments of energy across space, monopolies that resemble isolated magnetic charges, or domain walls acting as invisible boundaries between regions of the young cosmos. A cosmic texture stands apart from these. It has no single, concentrated form or sharp boundary at all. Instead, a texture is diffused over a wide area, a subtle tangle in the fields that permeate space. It is as if the universe tied a knot in itself, a knot without a tight core, one that eventually could slip loose. Crucially, a cosmic texture is not a permanent fixture of the cosmos. It cannot last forever. Over time, the knot in the energy field will eventually start to loosen and unwind, releasing its stored energy back into the fabric of space. When a cosmic texture finally unravels, it is like a coiled spring suddenly letting go, an abrupt but subtle release of tension in space itself. This act of untying has consequences for anything nearby, including the ancient light of the cosmic microwave background. Imagine a background photon wandering through space that happens to pass close to a texture at the very moment it is unwinding. The changing gravitational and energy conditions as the knot releases can give that photon a tiny push or pull, slightly altering its energy. Eons later, when that photon is collected by our telescopes, this effect appears as a faint anomaly in its temperature. In other words, the unwinding of a cosmic texture would leave a telltale sign on the sky, a patch of the cosmic background that is a bit hotter or colder than it would otherwise have been. When cosmologists first mapped the tiny temperature variations of the cosmic microwave background, they wondered if any of those spots could be signals from ancient textures. The cold spot, with its unusual size and depth, immediately stood out as a prime candidate. It wasn't just its rarity that made it intriguing, it was also the particular profile of the cold spot. It has a somewhat rounded, coherent shape and a measurable drop in temperature at its center. Features one might expect if a single event, like the collapse of a cosmic texture, had left its mark. In 2007, a group of researchers analyzed the cold spot and suggested that its properties were consistent with what a cosmic texture's imprint might look like. To them, this enormous cold region might indeed be the lingering evidence of a primordial knot untying itself billions of years ago, an echo of the universe's first moments. If the cold spot were truly caused by a cosmic texture, the implications would be staggering. It would mean that we have, in our sky, direct evidence of physics from a time so early that no star or atom had yet formed, a relic from perhaps a trillionth of a second after the Big Bang. Such a discovery would open a window into the highest energy processes imaginable, offering clues about how the fundamental forces of nature once unified, and then split into the distinct forces we know today. It would connect cosmology with particle physics in a way that nothing else currently can, revealing something about the grand story of how our universe came to be structured the way it is. Beyond the cold spot, the idea of cosmic textures existing at all raises many questions. How many such textures might have formed in the early universe? Are we seeing just one rare survivor, or could there be others lurking as more subtle patterns in the background? Theories allow for the possibility of multiple textures, each eventually unwinding and leaving their own marks. However, each unwinding would be a singular event happening randomly in space and time, so their imprints could be scattered and faint. The cold spot was the first and most obvious candidate. But if it was indeed born of a texture, it was natural to wonder if more evidence could be found by scouring the entire sky for similar anomalies. The cosmic texture hypothesis turned the cold spot from a mere curiosity into a testable prediction. It suggested that the cold spot was not a lone quirk, but part of a family of possible features produced by textures. If one texture had unwound in our observable universe, there might have been others. They might show up as additional unusually large spots, either hot or cold, somewhere in the CMB map. The hunt was on. Scientists now had to comb through the cosmic microwave background data with this idea in mind. Armed with theoretical templates for what a texture signature would look like, they aimed to discover whether the cold spot was unique or just the tip of an iceberg of primordial defects. This was a thrilling prospect. For decades, cosmologists had largely focused on refining our standard model of cosmology, one that includes dark matter, dark energy, inflation, and a nearly uniform early universe with tiny random fluctuations. That model has been extraordinarily successful in explaining observations. But the cold spot, if confirmed as the fingerprint of a cosmic texture, would be a sign of new physics beyond that standard picture. It would show that something extraordinary happened, something not captured in the simplest version of our cosmological story. It was a bold claim, and extraordinary claims require extraordinary evidence. Thus, While the cosmic texture theory for the cold spot was enticing, it had to face the rigorous scrutiny of observation and analysis. With stakes so high, the cosmic texture idea could not remain just an intriguing suggestion. It needed to be tested. The only way to know if this hypothesis held any truth was to confront it with more evidence. Scientists prepared to scrutinize the cosmic microwave background data more closely than ever, armed with the predictions of what textures might look like. If the cold spot were indeed a topological echo from the dawn of time, then perhaps other subtle texture signatures were hiding in the map, waiting to be discovered. If, on the other hand, no such signs could be found, then the cold spot might stand alone and force a different explanation for its existence. Either way, the quest now moved from speculation to data. It was time to let the evidence speak. The coming analysis would reveal whether the universe had indeed tied and untied knots in its early moments. Cosmic textures, if they exist, would be relics of an early universe event known as symmetry breaking. In the first tiny fraction of a second after the Big Bang, it's believed that the unified forces of nature separated into distinct forces, analogous to how a cooling metal might suddenly become magnetic when its atoms align, or how water freezes and crystals form, if that process of symmetry breaking wasn't perfectly uniform everywhere. It could have left behind defects in the energy field filling space. Most cosmological models, like the inflation theory, assume such defects either never formed in significant numbers or were stretched away. That's why detecting a texture today would be so extraordinary. It would challenge some assumptions and shine a light on physics at energies far beyond what we can achieve on Earth. The data analysis that followed turned into a quiet yet profound adventure in cosmology. Having a compelling hypothesis is one thing, but science demands proof. If a cosmic texture had indeed left its fingerprint on the sky, researchers needed to unearth more evidence for it. The cold spot by itself was suggestive, but one lone anomaly could always be a coincidence. The challenge set before the cosmologists was clear. Search the entire cosmic microwave background map for any additional signs that might confirm the presence of cosmic textures. It was a bit like sifting through sand for a few hidden, precious gems, where the gems were subtle patterns hidden in a vast sea of cosmic noise. Teams of scientists got to work, armed with data from NASA's Wilkinson Microwave Anisotropy Probe, WMAP, satellite, which had mapped the microwave sky with unprecedented precision. The task was to scan this map for telltale texture imprints. But what exactly were they looking for? A cosmic texture's signature would likely appear as a circular or nearly circular spot, either slightly cooler or slightly warmer than the surroundings, with a particular profile, a gentle change in temperature from the center of the spot to its edges. The cold spot itself fits this description fairly well, but to truly test the theory, they needed to see if other, perhaps smaller or less obvious, spots of this kind were scattered elsewhere on the sky. This was easier said than done. Imagine examining a world map covered in random ink splatters, trying to find perfect circles. The human eye can play tricks, seeing patterns where none truly exist. A blotch or a blur might look like a circle one moment, and like nothing in particular the next. To avoid fooling themselves, the researchers relied on algorithms, mathematical pattern finders that could systematically comb through the data without bias. They programmed computers to simulate the cosmic microwave background many times over, generating fake skies based on the standard cosmological model without any textures. By comparing these simulations with the actual sky map, the algorithms could pick out anomalies that stood out above the random noise. One approach was to essentially slide a filter across the sky, a template of a round spot in various sizes that could match what a texture imprint would look like. At each position on the map and at each scale, they asked, "Does the sky here resemble the kind of spot a texture would produce?" It was an enormous search, considering all possible locations and sizes of spots, and it pushed the limits of computational power available at the time. Each potential hit, each place that vaguely looked like a texture's footprint, had to be assessed for how likely it was to appear by chance. The vast majority of potential spots that turned up in this automated search were not particularly significant. They were about as common as one would expect from random fluctuations. Still, among all those billions of pixels of data, the cold spot remained the most conspicuous oddball. In the initial pass with WMAP data, no other feature quite like it jumped out. Scientists found that aside from the cold spot, the microwave sky was generally consistent with the random speckles predicted by the standard model of cosmology. If textures had been abundant in the early universe, the analysis should have uncovered not just one, but many unusual spots. The absence of a crowd of such features was telling. In statistical terms, it allowed cosmologists to set an upper limit on how many textures could be out there. The results indicated that textures, if they exist at all, must be exceedingly rare. By 2012, the first thorough, full-sky search for cosmic textures was completed, and the findings were sobering. Aside from the cold spot itself, there was no clear evidence of any other texture-like signatures in the WMAP data. The researchers reported that their analysis could rule out any theoretical model that predicted a large number of textures. In technical terms, if a theory suggested that a dozen textures should have formed across the sky, that theory now looked very unlikely. The data simply did not show that many unusual spots. Their report placed a confidence limit, saying in effect, "We can be 95% sure that there aren't more than a handful of texture imprints in our observable universe." In everyday terms, that meant if the cold spot was indeed caused by a cosmic texture, it might well be one of the only ones of its kind, a cosmic rarity. For those who had hoped the cold spot would be just one piece of a larger pattern, this result was a clear reality check. This outcome was both a relief and a disappointment, depending on whom you asked. On one hand, the standard cosmological model, the one without exotic textures, had weathered the challenge. The absence of multiple texture signals meant that the simple, elegant picture of the early universe, seeded by random fluctuations and stretched out by inflation, was still holding strong. There was no immediate need to rewrite the cosmology textbooks. On the other hand, the mystery of the cold spot persisted. If it was unique, then understanding it might require a unique explanation. The texture hypothesis was not entirely ruled out, but it no longer had the support of a pattern of similar spots elsewhere. It was as if nature had left just one enigmatic clue, and no others to back it up. Scientists did not stop with WMAP. The Planck satellite, launched by the European Space Agency, took the quest a step further a couple of years later. Planck measured the cosmic microwave background with even higher resolution and sensitivity, providing an even sharper view of the sky. If any small texture-like features had been hiding just below WMAP's detection threshold, Planck was designed to sniff them out. When Planck's full sky maps were released, cosmologists eagerly repeated the texture search on this pristine new data. The cold spot was still there, a confirmed feature, not an artifact of measurement, but the story for textures remained unchanged. Planck, like WMAP, did not reveal a troop of lesser cold spots or hot spots that would scream textures from the early universe. The cold spot stood alone in its strangeness. This painstaking scrutiny of the sky did have a silver lining. By not finding abundant evidence of textures, scientists managed to place new constraints on theories of the early universe. Some exotic ideas about how the universe's earliest phase transitions occurred were now less plausible, as they would have generated more textures than we see. Conversely, if there is a theory that yields perhaps just one texture in the observable universe, the cold spot might fit comfortably into that narrative. But such a theory would require a strange fine-tuning of fate, making our patch of the universe special in a way that cosmologists usually resist accepting without strong evidence. After years of searching, the conclusion was tantalizingly inconclusive. The cold spot could be a texture, but if so, it's a lone one in our sky, making it a very improbable event under most models. Alternatively, it could be that the cold spot is not a texture at all, and something else entirely is responsible, something that doesn't produce multiple clones of itself across the heavens. In science, ruling out possibilities is as important as confirming them. The searches with WMAP and Planck effectively ruled out a whole class of theories that predicted numerous texture imprints. What remained was either the possibility of a one-off texture arising from highly unusual initial conditions, or the need for a different explanation altogether. Through this meticulous testing of the texture hypothesis, one thing became clear. The cold spot was not going to give up its secrets easily. The initial excitement of the cosmic texture idea had met the hard scrutiny of data, and the universe replied with a bemused silence. No chorus of texture signals echoed across the sky. Only that single, solitary note, the cold spot itself, lingering mysteriously. If it was truly an echo from the dawn of time, it was a lonely one. And if it was not, then the cosmic microwave background was teasing us with a chance coincidence, or pointing to some other new physics not yet understood. In the aftermath of these searches, cosmologists found themselves both wiser and more perplexed. They had learned how to push their data analysis techniques to new limits, how to carefully distinguish real features from imagined ones, and how to extract meaningful constraints on theoretical ideas. Yet, the fundamental question remained unanswered. What is the cold spot telling us? The texture test had come back negative for the most part, but the test itself taught valuable lessons. It showed that our universe, in its vast expanse, mostly behaves as expected. Mostly, but not entirely. It is that small deviation from the ordinary, that stubborn cold spot, that continues to intrigue and trouble the minds of scientists. If the cold spot wasn't accompanied by an army of other textures, then perhaps the key to its existence lay elsewhere. Scientists began to consider other possibilities with renewed interest. Maybe the anomaly wasn't born in the ultra-early universe after all. Perhaps something closer to home, in cosmic terms, could be the cause. Or maybe there were entirely different new physics at play, ones that would not leave multiple imprints, but could still produce one grand cosmic oddity. In grappling with the negative result of the texture search, researchers effectively cleared the ground of one hypothesis. This made room for them to explore other ideas with greater attention. The journey was far from over. The cold spot remained, as ever, an invitation to further discovery, urging us to look deeper and think harder about the universe's hidden corners. The cold spot is not the only puzzle hiding in the cosmic microwave background. As scientists delved deeper into the data, they found that our universe's baby picture contained a few other irregularities, subtle fingerprints that did not quite fit the pristine random pattern predicted by theory. These strange features became additional clues, hinting that something might be amiss or incomplete in our understanding. Each anomaly by itself is small, and none shout as loudly as the cold spot, but together they form a chorus of whispers, suggesting that the universe may have a few secrets left in its earliest chapters. One of these curious features has been nicknamed the axis of evil, a dramatic moniker for a subtle oddity. When cosmologists analyze the largest scales of the microwave background map, They expected the hot and cold spots to be oriented randomly, with no particular direction preferred over another. The universe, after all, has no up or down, no special axis. At least, it shouldn't. But to their surprise, the biggest fluctuations in the CMB, patterns spanning huge swaths of the sky, seem to have a strange alignment. Imagine looking at the ripples on a pond and noticing that the biggest ripples all line up in one direction, as if pointing toward the same compass point. That's roughly what the axis of evil refers to. The observed alignment of the cosmic microwave background's largest temperature variations along a certain axis across the sky. This axis runs through the celestial sphere in a way that intriguingly lines up with the plane of our solar system, which made some scientists initially suspect a measurement artifact. Perhaps some leftover glow from the solar system or our galaxy was contaminating the data, skewing the patterns. Yet, even after careful cleaning of the data, the alignment persisted, leaving cosmologists scratching their heads. It was an uncomfortable result. In this context, evil was not meant literally. It signified that the finding threatened a cherished cosmic principle, isotropy, the idea that the universe looks the same in all directions. If the alignment were real and not a fluke, it might imply that there's something about the geometry or initial conditions of the universe that sets a preferred direction. Such a notion borders on the heretical in standard cosmology. Another odd hint comes from a simple question. Does one half of the sky look like the other half? For a nearly uniform universe, the answer should be yes. Take any way you split the sky, the total variations in the CMB on one side should statistically mirror those on the other. Yet researchers noticed a slight imbalance. One hemisphere of the sky, defined in a particular way, shows marginally stronger fluctuations than the opposite hemisphere. It's as though the cosmos has a faint, two-faced quality. A northern side and a southern side that aren't perfectly alike. This is called the hemispherical power asymmetry. The difference is small, and it's tricky to measure. Still, it appears to be there in the data, nudging us to wonder if the cosmic principle of no preferred direction might have its exceptions. Could it be that our observable universe, by sheer accident, happened to have a bit more primordial lumpiness on one side? Or is there physics at play that made one half of the newborn universe ever so slightly different from the other? Then there's the mystery of the low power on large scales. When scientists look at the CMB, they analyze it in terms of patterns of different sizes. The theory of inflation, our best explanation for the early universe's rapid expansion, predicts how strong the fluctuations should be on various scales. By and large, it's spot on. But at the very largest scales, patterns that span the entire sky, the observed fluctuations are weaker than expected. In particular, the so-called quadrupole, a pattern that divides the sky into 4 alternating patches of high and low temperature, is unusually faint. It's as if the broadest brushstrokes of the universe's baby picture were painted a little too lightly. By itself, this large-scale quirk could be shrugged off as a statistical fluke. But taken together with the other curiosities, it adds to an uneasy feeling that the cosmos is just a bit stranger than expected. Some wonder if these anomalies, collectively, hint at new physics, while others suspect we may simply be encountering the inevitable oddities that random chance produces. Either way, the coincidence of multiple anomalies keeps the questions alive. Scientists have approached these anomalies with cautious fascination. Each could be nothing more than random chance. After all, in any random pattern, some lines will appear to align by coincidence, and some areas will look a bit different than others. There's a risk of overinterpreting noise, of seeing faces in the clouds. And indeed, a majority of cosmologists lean toward the view that most of these large-scale anomalies, tantalizing though they are, may well be statistical flukes or the result of unaccounted systematic errors. But not everyone is content with that shrug. The fact that multiple independent oddities exist in the same data set gives pause. It's like walking into an old house and finding a door slightly ajar, a window unlatched, and a book fallen off a shelf. Any one of those could be a coincidence, but together you start wondering if something more is going on. For the cold spot especially, alternative explanations have garnered significant attention. If it isn't a cosmic texture, what else could have made this region of the sky cooler than expected? One down-to-earth possibility is that the cold spot isn't telling us about the dawn of time at all, but rather about a structure much closer to us. In 2007, a group of astronomers proposed that a colossal supervoid, an enormous region of space with far fewer galaxies than average, lies between us and the cold spot area of the CMB. If true, this great void would be billions of light years across, making it by far the largest known void in the universe. How could such emptiness make the cosmic microwave background appear colder? The answer lies in the subtle dance of light and gravity. As cosmic microwave background photons journey toward us, they sometimes pass through large clusters of galaxies, or, conversely, through vast empty voids. When a photon falls into the gravitational well of a massive cluster, it gains a bit of energy, getting blue-shifted, and as it climbs back out, it loses that energy, ending up roughly where it started. In an expanding universe, however, this balance can tip. If the universe is accelerating due to dark energy, a photon climbing out of a gravitational well late in time doesn't quite lose all the energy it gained falling in, because the well itself has stretched and shallowed by the time it leaves. Conversely, if a photon traverses a great void, it loses energy going in and gains some back coming out. However, if the void's depth diminishes during the photon's transit, the photon doesn't regain everything it lost. The net result is that the photon emerges a bit less energetic, in other words, cooler, than it would have been otherwise. This phenomenon is a version of the integrated Sachs-Wolf effect, a way that evolving cosmic structures imprint on the CMB. If a supervoid of extraordinary size sits in front of the cold spot area, it could potentially account for part of the temperature dip we see. Surveys of galaxies have indeed hinted at something unusual in that direction of the sky. Radio telescope maps once noted a decrease in the density of distant radio sources toward the cold spot, and later, other studies using infrared and optical surveys reported evidence of a vast underdense region. Astronomers sometimes call it the Eridanus supervoid, named after the constellation in which the cold spot lies. One study in the mid-2010s claimed to find a void roughly 1.8 billion light-years across, centered a few billion light-years away from us, lining up with the cold spot's position. If this is real, it's a stunning structure in its own right, a cosmic cavern nearly empty of the usual galaxies and matter. Such a void would rank among the largest cosmic structures ever identified. However, even a void of that magnitude might not fully explain the cold spot's chill. Detailed calculations bear this out. They indicate that while a giant void would indeed make that patch of the CMB a bit colder, it likely falls short of accounting for the full observed dip in temperature. In other words, a supervoid might be part of the story, but not the whole story. Additionally, the very existence of such a gargantuan void is contentious. Our universe's structure formation models allow voids, but a void that large is at the extreme tail of probability, much like the cold spot itself. Some galaxy surveys have questioned whether the apparent supervoid is truly as empty as initially reported, or whether the statistical significance of the void's detection is robust. Like the cold spot, the void claim stands out and invites skepticism and further verification. Or perhaps these anomalies are hints of something fundamentally new, like a non-trivial cosmic topology or an imprint from before inflation. As it stands, the alignments and asymmetries remain unresolved curiosities. They could still turn out to be mere statistical flukes, or they might point to physics beyond our current understanding. For now, they keep scientists wondering and questioning their assumptions. On the more exotic end of possibilities lies a hypothesis that sounds like science fiction: the cold spot as a bruise from another universe. In the framework of cosmic inflation, it's conceivable that our universe is just one bubble among a potentially vast multiverse of other bubble universes. If two bubbles collided early in their expansion, they might disturb each other's contents. Picture two soap bubbles drifting and gently bumping. They might create a circular patch or distortion where they touched. Some theorists have speculated that such a collision could leave a circular blemish on the cosmic microwave background, perhaps a region of slightly lower temperature. The cold spot's roughly circular, isolated nature made it a tempting target for this idea. Could it be the aftermath of our young universe colliding with another bubble universe long ago, imprinting a cool region in the radiation we observe today? This multiverse collision scenario is highly speculative, but it fired imaginations. Remarkably, it was an idea that could be tested by physicists, at least in principle. Cosmologists developed algorithms to hunt for disk-like patterns in the CMB data that might indicate collisions between universes. They scanned WMAP and later Planck maps for telltale signatures of such cosmic bruises. What they found was, again, not a smoking gun, but a few intriguing candidates. And one of them was indeed the cold spot. The cold spot showed up in these searches as one of the largest and most significant circular anomalies. However, the evidence was not strong enough to declare a detection of a bubble collision. The odds that such a pattern could arise by chance were not low enough to rule out a fluke definitively. So while the cold spot did nothing to disprove the multiverse idea, it didn't confirm it either. The multiverse explanation remains a fascinating, if unprovable, possibility. Faced with these various clues, alignments, asymmetries, voids, and even whispers of other universes, cosmologists have been both humbled and inspired. Humbled because the universe has once again reminded us that it may not conform perfectly to our neatest models. Inspired because every anomaly is an opportunity to discover something new. Each anomaly rekindles the drive to probe further and understand the cosmos more deeply. Each proposed explanation for the cold spot or related anomalies, whether prosaic or profound, spurs new research. Astronomers design sharper surveys to map galaxies and find voids or confirm their absence. Physicists refine their models of inflation to see if a small tweak could produce an outsized cold region or an alignment of patterns. Some have wondered if a non-standard period in the early universe, say an exotic physics phase transition or a subtle energy field, might cause not one, but a set of anomalies, tying them together under one theoretical umbrella. In essence, the anomalies have kept the field on its toes. As of now, none of the alternative theories for the cold spot or the other CMB curiosities has emerged as a clear winner. The void explanation has its merits, but doesn't seem to entirely solve the puzzle. The texture theory, as we explored, is heavily constrained, and alone doesn't look likely unless we're extraordinarily lucky to have just one in view. The chance alignment or statistical fluke interpretation is still very much on the table, unsatisfying to some, but a real possibility given the large cosmic canvas we're drawing from. The multiverse collision idea, while captivating, may forever lie in the realm of the untestable, unless some other observable imprint of another universe is found, and the axial alignment and hemispheric differences remain unresolved curiosities. Perhaps trivial after all, or perhaps hints of something fundamentally new. What these clues have done is keep the dialogue open. They remind us that even in an era often dubbed the precision cosmology age, where we've measured cosmic parameters to high accuracy, there are still mysteries lurking at the edges of our maps. The cosmic microwave background, for all its wealth of information, still has a few smudges and oddities that make scientists furrow their brows and ponder. With each new dataset, they eagerly check, is the cold spot still there? Yes, it always is. Has it changed? No, it remains as it was, a fixed feature of our sky. Do the anomalies persist in new observations? Yes, Planck saw the same odd alignments and asymmetries as WMAP, confirming they are not mere artifacts of one satellite. Perhaps the next breakthroughs will come from new kinds of observations. Future missions might measure the polarization of the CMB even more precisely, potentially unveiling subtle traces of whatever caused the cold spot, though there is no guarantee. Large-scale surveys of galaxies and cosmic structures, ever growing in scope, could either discover more megavoids, strengthening the void case, or show that our neighborhood isn't so special after all. Or maybe a completely different cosmic messenger, say, primordial gravitational waves, or the cosmic neutrino background, could one day reveal clues about unusual events in the early universe that left imprints like the cold spot. These ideas are speculative threads, but science often progresses by tugging on such threads to see what unravels. In this way, the cold spot has evolved from a peculiar blotch on a map into a central character in cosmology's ongoing story. It is a challenge thrown down by the cosmos. Explain this, if you can. Alongside its fellow anomalies, it keeps cosmologists from resting easy, ensuring that we continue to test the limits of our theories and the reach of our observations. Each clue in the CMB is a reminder that the book of the universe is not yet fully written. There are footnotes and enigmatic passages that require further interpretation. And as long as those mysteries endure, scientists will continue the quest, driven by the hope that even the strangest cosmic cold spot can ultimately be illuminated by human curiosity and ingenuity. As our journey through cosmic mysteries continues, we turn our gaze to one of the most confounding phenomena ever conceived, the black hole. Long before modern science gave this darkness a name, the idea of a star so massive that it trapped its own light flickered in the minds of a few bold thinkers. Centuries ago, under candlelight and through crude telescopes, early scientists dreamed of what they called dark stars, invisible giants lurking in the depths of space. These dark stars were purely speculative, whispered about in scholarly letters and journals. But even then, the notion carried a mesmerizing allure, an object so heavy, so powerful, that not even a beam of light could break free from its grip. In the late 18th century, an English natural philosopher, John Michell, mused about such a possibility. He imagined a star much larger than our sun, so large and dense that its gravity would be overwhelming. This gentleman, living in an era of carriage rides and oil lamps, dared to propose that a sufficiently massive star's pull might be so intense that it could yank back the very light it emitted. If light behaved like tiny particles, he reasoned, and if gravity tugged on those particles, then an enormous star could become a trap of light, forever cloaked in darkness. At the time, this idea was a curious footnote, a thought experiment at the fringes of understanding. Most of Michel's contemporaries smiled at the fancy, or simply looked away, unconvinced that nature would allow such a bizarre creature to exist. Little did he realize, he was offering a first glimpse at a phenomenon that would challenge our understanding of reality. For a long time, his notion remained an almost forgotten footnote, quietly waiting for a new era of science to rediscover it. Across the English Channel, a French mathematician independently arrived at a similar strange conclusion. In the twilight of the 18th century, Pierre-Simon Laplace even wrote of such invisible stars in 1796, speculating that gravity might render them unseen. He included the idea in early editions of his work, though he quietly removed it as the wave theory of light gained favour. For a moment, the idea of these hidden heavy stars captured some attention. But like shadows at dawn, these early thoughts of dark stars soon faded. The science of the day was changing. Light was coming to be seen not as a stream of particles that gravity could grab, but as a wave moving through the ether, seemingly beyond the reach of gravity's pull. If light had no substance, how could gravity hold it captive? And so, throughout the 1800s, the vision of dark stars slipped into obscurity. It became a forgotten ghost story of science, tucked away in old books, rarely spoken of as astronomy, marched forward with new discoveries that focused on things that could be seen and measured. For nearly a century, the universe's darkest secret remained just that, a secret, hiding in plain theoretical sight. But the cosmos has a way of revealing its wonders to those who persist in asking questions. At the dawn of the 20th century, a revolution in physics was underway. Space and time, gravity and light were about to be woven together in a way those early dreamers of dark stars could never have imagined. It was Albert Einstein's theory of general relativity, introduced in 1915, that reopened the door to these lost ideas. Einstein's equations described gravity not as a force grabbing at objects, but as a bending of space-time itself. Planets orbit not because the sun reaches out and pulls them, but because the space around the sun curves and guides them along a path. In this new picture of gravity, scientists began to wonder, could Einstein's cosmic fabric fold in on itself so tightly that it creates a pit from which nothing can escape? The math said yes. While the First World War raged across Europe, a lone German soldier scientist worked on Einstein's equations from the depths of the trenches. Amid mud and conflict, Karl Schwarzschild managed to focus his mind on the mysteries of gravity. In 1916, by the dim light of a lantern and with artillery thunder in the distance, he discovered something remarkable about gravity itself. He sent his results from the battlefield back to Einstein, a letter that would astonish the scientific world. Beyond a certain boundary, now known as the event horizon, Schwarzschild found that nothing, not even light, could climb out of a sufficiently compact mass's gravitational well. Schwarzschild's solution was like a theoretical echo of those old dark star musings, but now grounded in the rigorous mathematics of general relativity. Here it was, a black hole in the equations, a region of pure night from which no information could return. Schwarzschild's revelations, derived in wartime, took time to percolate through the scientific community. Coming as it did on the eve of a world war, this profound insight remained largely on paper for years, waiting for the space age to bring it back to the forefront of science. At first, his result was met with fascination, but also deep skepticism. Even Einstein himself found the idea perplexing and unsettling. Could nature really allow such an abyss to form in reality? For decades, The concept of these frozen stars, as some called them, remained a mathematical oddity. Many scientists believed that in the real universe, something would always intervene to prevent a full collapse into such a gravitational trap. Some proposed that a spinning star might tear itself apart or shed mass before crossing that final point of no return. Others thought perhaps the mathematics was deceiving, that maybe nothing could truly become infinite or singular as the equations suggested. Yet, step by step, evidence and further theoretical work kept pointing back to the existence of these gravitational abysses. In the 1930s, a young Indian astrophysicist named Subrahmanyan Chandrasekhar discovered that there was an upper limit to how much mass a dying star's core could support. If a star's remnant was heavier than about 1.5 times our Sun, nothing known, no degenerate pressure of electrons, could hold it up once its nuclear fires burned out. It would collapse under its own weight, inevitably. Around the same time, others pondered what would become of the core of a massive star after it ended its life in a supernova explosion. In 1939, J. Robert Oppenheimer and his student Hartland Snyder used Einstein's equations to show that if a star were massive enough, no force could halt its collapse. The star would keep shrinking and compressing, down past even the size that atomic forces could support, effectively vanishing from view behind an invisible boundary. Coming as it did on the eve of a world war, this insight remained a theoretical curiosity for decades, quietly waiting for the space age to bring it to the forefront. These calculations painted a stark portrait. Massive stars could die by turning into something like a bottomless well in space-time. Still, even as the equations spoke, the idea remained remote from everyday astronomy. During the mid-20th century, the world had more immediate concerns, and the notion of black holes, though the term itself wasn't coined yet, lurked on the scientific fringes. Many physicists regarded the collapse calculations as correct on paper, but too strange to be physically real. The Second World War came and went. The atomic age dawned, ironically led by Oppenheimer himself, and humanity looked to the stars with new eyes. Rocketry and early space exploration captured the public's imagination. Meanwhile, out in the theoretical frontiers, a few researchers kept circling the riddle of the dark stars. It wasn't until the 1960s that these mysterious objects stepped out from theory into the beginnings of reality. A new generation of physicists and astronomers, armed with better technology and a post-war hunger for discovery, started hunting for the extraordinary. In 1965, a British physicist named Roger Penrose published a groundbreaking proof. He showed that once a certain point was passed in a gravitational collapse, a singularity, a point of infinite density, must form inside. His mathematics implied that black holes weren't just quirks of an equation. Under the right conditions, they could form naturally and inevitably. Around the same time, the influential American physicist John Wheeler gave these objects a name that stuck. Black holes, he called them, capturing the imagination of scientists and the public alike. The era of the dark star had been reborn in a new scientific light, and this time, humanity was prepared to search the skies for the real thing. The stage was set. The concept of black holes, once an idle curiosity, had matured into a serious scientific question. Theoretical groundwork suggested that nature not only allowed black holes, but might even be creating them in abundance, perhaps in the hearts of dying stars, or lurking quietly in the centers of galaxies. But saying that black holes could exist was one thing. Finding actual evidence of these one-way doors in space was another challenge entirely. How do you detect the invisible? How do you perceive a thing that, by its very nature, emits no light and shrouds itself from view? It was a puzzle that astronomers were now eager to solve. In the coming years, they would begin chasing clues, seeking indirect signs of these cosmic abysses. The hunt for the shadows of the black holes, their telltale gravitational effects, was about to begin, turning speculation into discovery. It did not take long for the first clues to appear. In 1964, a sounding rocket experiment briefly detected an unexpected surge of X-rays from the direction of the constellation Cygnus, hinting at something extraordinary out there. By the late 1960s, new technology was beginning to pierce the veil of cosmic invisibility. Astronomers discovered a persistent, intense X-ray source coming from a hidden object in the constellation of Cygnus. This mysterious beacon, dubbed Cygnus X1, flickered and flared with high-energy light that no ordinary star could produce. What could shine so brightly in X-rays, yet remain unseen in visible light? As researchers pointed more instruments towards Cygnus X1, evidence mounted that they were witnessing the signature of a black hole's presence, not seen directly, but inferred from the chaos it caused around it. Cygnus X1 became a celestial laboratory for understanding black holes. In visible light, astronomers found a giant blue star dancing in a tight orbit with an invisible partner. The blue star swayed and wobbled, tugged by an enormous gravitational force. Calculations revealed that the hidden companion had a mass perhaps 10 or even 20 times that of our Sun, far too massive and compact to be a normal star, or even a neutron star. It was a strong contender for a true black hole. Matter from the blue star was being siphoned off, spiraling into the darkness around the unseen object. As this gas whirlpooled inward, it heated to millions of degrees, emitting powerful X-rays before vanishing beyond the point of no return. In those X-ray flickers, humanity had found a kind of silhouette, an indirect shadow of a black hole. The idea of actually confirming a black hole's existence electrified the scientific community. Yet, some remained cautious, wanting more proof before declaring victory. The renowned physicist Stephen Hawking even made a playful bet in the early 1970s with his colleague Kip Thorne about the true nature of Cygnus X1. Hawking, ever the contrarian at that moment, bet against it being a black hole, partly in jest, hedging his scientific bets. As years passed and more data poured in, the evidence became overwhelming. Cygnus X1 was all but confirmed as a black hole, and Hawking, with good humour, conceded the bet in 1990. It was a moment both light-hearted and profound. One of the universe's darkest secrets was no longer just a theoretical spectre, but a real object influencing the dance of stars. Encouraged by the discovery of Cygnus X1, astronomers scoured the skies for other hidden heavyweights. Before long, they found more X-ray binaries, pairs of stars where one member is invisible yet immensely heavy. One by one, these systems revealed themselves. A visible star orbiting a dark companion that feasts on stellar gas. Each time, the pattern was similar. An unseen object, likely a black hole, gravitationally dominating its companion and lighting up the X-ray sky as it consumed matter. These discoveries in the 1970s and 1980s established a new reality. Black holes were not rare monsters confined to speculation. They were out there, sprinkled among the stars, quietly, and sometimes not so quietly, going about their lethal business. While X-rays let us infer black holes through their voracious appetites, another cosmic messenger would soon open a completely new window onto these dark phenomena. For a century after Einstein's predictions, physicists had been striving to detect gravitational waves, ripples in the very fabric of spacetime caused by massive objects in motion. Black holes, with their intense gravity, were prime candidates to create such waves, especially when they collided with each other. Generations of scientists built ever more sensitive instruments, listening for the symphony of spacetime. In the mid-2010s, their patience was rewarded. In a quiet moment in September 2015, a subtle tremor passed through the Earth, far too subtle for any human to feel, yet unmistakable to the sophisticated lasers of the LIGO Observatory. The signal lasted only a fraction of a second, but its pattern was unlike anything caused by local noise. It was the characteristic chirp that scientists had anticipated, the final fleeting sound of two massive black holes spiraling together and merging. Each black hole was around 30 times the Sun's mass, and as they collided, they briefly emitted more energy in gravitational waves than all the stars in the universe combined. This momentary ripple, traveling over 1 billion light-years, stretched and squeezed space by a tiny amount, enough for LIGO's detectors to record. When the announcement came in early 2016, it marked the first direct evidence of black holes merging, an astrophysical drama heard rather than seen. At long last, we had heard the sound of invisible giants crashing in the dark. The confirmation of Einstein's century-old prediction electrified the scientific community and marked the dawn of gravitational wave astronomy. It was a triumph of human ingenuity and the beginning of a new era of exploration in astronomy. This discovery was transformative. It was as if the universe had spoken a new language, a language of gravity, and we had finally learned to listen. Over the following years, LIGO and its European partner Virgo heard many more such songs from the darkness. Pairs of black holes swirled and merged in distant galaxies, sending out faint echoes of their existence across the cosmos. Some collisions were surprisingly massive, yielding new black holes of hundreds of suns, hinting at an intermediate class of black holes between the stellar and the supermassive. Astronomers even caught gravitational whispers of a black hole swallowing a neutron star. Each detection was a revelation, confirming that black holes were not rare cosmic curiosities, but common characters in the grand ballet of the universe. And with each gravitational wave, we gleaned new insights about black hole masses and spins, and into gravity's behavior under extreme conditions. From X-ray flickers in far-off star systems to gravitational waves rippling across space, and finally to a direct portrait of a cosmic abyss. The journey of uncovering real black holes transformed these objects from theory into tangible reality. Yet, even as we celebrate how far we've come in illuminating the darkness, we are reminded that every answer uncovers new questions. Seeing a black hole's shadow raises puzzles about how matter behaves at the brink of oblivion. Hearing black holes collide makes us wonder what extreme secrets are encoded in those waves. The quest to understand black holes, it seems, only deepens the mystery. But for now, humanity had finally pulled back a corner of the cosmic curtain, catching a glimpse of these dark wonders that had lurked, unseen for so long. By the closing decades of the 20th century, black holes were no longer mere theory. They had become observable reality through X-rays and gravitational waves. Yet an even greater revelation was on the horizon. Evidence began to suggest that nearly every large galaxy harbors a colossal black hole at its center. The cosmic focus shifted to these galactic cores, where new kinds of gravitational giants lay in wait. High above the plane of our galaxy, early on a crisp night in 1963, a young astronomer carefully examined a faint, star-like point in the sky that defied easy explanation. Its spectrum, the rainbow signature of its light, was unlike any ordinary star. This object, later named 3C273, turned out to be not a star at all, but something far more powerful, the extremely bright heart of a distant galaxy. It was the first identified quasar, a quasi-stellar object shining with an intensity that dwarfed entire galaxies, sometimes shining hundreds of times brighter than an entire Milky Way's worth of stars. What could possibly power such brilliance? Before long, scientists concluded that only one engine could do it: a supermassive black hole gorging on infalling gas, unleashing torrents of energy. This was a radical realization, that black holes could sit at the centers of galaxies, billions of light years away, and announce their presence through vast beacons of light. The notion of supermassive black holes, giants millions or even billions of times more massive than the Sun, soon moved from speculation to a central idea in astrophysics. In the decades that followed the quasar discovery, evidence mounted that these cosmic heavyweights lurk in the cores of most large galaxies, not just in rare, dramatically active ones. Some galaxies, like our own Milky Way, appeared relatively quiet, without the glaring beacon of a quasar. Yet even in these calmer galactic centers, subtle clues hinted at a hidden presence. Astronomers detected unusual motions of stars and gas deep in their cores. It was as if an invisible gravitational anchor was yanking stars around at breathtaking speeds. The only object dense and massive enough to cause such commotion without shining any light of its own was a supermassive black hole. Our Milky Way provided a front-row case study. For years, a faint radio source named Sagittarius A, located at the galaxy's core, intrigued scientists. In the 1990s, teams of astronomers began tracking the movements of stars near this mysterious radio spot with unprecedented precision. What they saw was astonishing. Stars whipping around an unseen object, moving as fast as a few thousand kilometers per second. One star, later named S2, was observed to swing in a highly elliptical orbit, coming as close as just a light day or two from the center, a hair's breadth on cosmic scales, before slingshotting away again. By plotting these orbits, scientists could weigh the central object using the laws of gravity. The result was mind-boggling. An object about 4 million times the mass of our Sun dwelt at the center of the Milky Way, confined to a region no larger than our solar system. There was virtually no doubt left. This was our galaxy's own supermassive black hole. This discovery was a triumph of modern astronomy, turning what had once been an outlandish conjecture into concrete reality. The idea that a monstrous black hole sits quietly at the heart of the Milky Way, and by extension, similar behemoths in countless other galaxies, reshaped our understanding of the cosmos. In 2020, this achievement earned astronomers Andrea Ghez and Reinhard Genzel a share of the Nobel Prize, a testament to how far the concept of black holes had come. What's more, the Milky Way's central black hole, though currently a gentle giant, likely had a more tempestuous youth. Evidence suggests that in the past, it devoured material more voraciously, perhaps briefly turning our galaxy's core into a mini-quasar or blasting out energetic jets. Even today, it's not entirely dormant. Occasional flares of X-rays and infrared light betray flickers of activity as it snacks on some stray gas or an unlucky asteroid. Such episodes show that even a sleeping giant can stir. If our galaxy's black hole is relatively modest, at a few million solar masses, other galaxies harbour far more monstrous specimens. In giant elliptical galaxies, especially those at the centres of galaxy clusters, black holes reaching billions of solar masses are thought to be commonplace. The galaxy M87, the same one that gave us the first black hole image, contains a black hole of roughly 6.5 billion suns, a true leviathan. Observations of M87 over many decades revealed a narrow jet of particles shooting out from its core at near light speed, a dramatic byproduct of the black hole's feast, as magnetic fields channel some of the infalling matter back out into space. And M87 is far from the extreme. Astronomers have identified quasars so distant and brilliant that their black holes must be tens of billions of solar masses. These ultramassive black holes strain our imagination. How could something grow so colossal within the age of the universe? Their very existence challenges theories of black hole formation and growth, hinting at violent, fast-paced beginnings or exotic physics in the early cosmos. There is even speculation that some black holes might be relics from the very birth of the universe. In the chaotic, high-density moments just after the Big Bang, tiny pockets of matter could, in theory, have collapsed into minuscule black holes. These hypothetical, primordial black holes would be far smaller than stellar black holes, perhaps as small as asteroids, yet still incredibly massive for their size. None have been confirmed, but if they exist, they might drift through galaxies unseen, even contributing to the elusive dark matter that binds the cosmos together. Supermassive black holes are not mere passive sinkholes. They are dynamic players on the cosmic stage. When they devour matter, they can become the central engines of active galactic nuclei, releasing immense energy in the form of radiation, particle jets, and winds. This outpouring can influence an entire galaxy. Think of a galactic center blasting out radiation and gusts of particles that can heat up or sweep away interstellar gas in the core. Such feedback can regulate or even quench the formation of new stars. In effect, a black hole of millions or billions of suns can govern the life of a galaxy that is trillions of times its size. Over time, an intriguing pattern emerged. The mass of a galaxy's central black hole is closely linked with the size and velocity dispersion of the galaxy's bulge of stars. It's as if the growth of a galaxy and the growth of its black hole go hand in hand, each influencing the other across cosmic time. Through decades of observation, astronomers have found evidence that most galaxies, from spirals like our own to giant ellipticals, house dark giants in their cores, sometimes blazing as quasars, other times lying in wait. We now understand that black holes are fundamental components of galaxies, not rare anomalies. They can shape their surroundings, unleashing jets and winds that can trigger or halt the birth of stars. And yet, for all we have learned about these cosmic giants, profound mysteries remain. Chief among them is a simple, unanswered question: what truly lies inside a black hole? At the center of every black hole, hidden behind the veil of the event horizon, our current understanding of physics comes to a halt. This brings us to the ultimate enigma. We can map the dance of stars around black holes and capture images of their shadows, but we cannot peer beyond that one-way boundary. As we consider these mighty gravitational giants, our curiosity naturally turns inward, past the point of no return. In the next part of our journey, we venture not outward to see where black holes are, but inward to confront the question of what happens deep inside these mysterious abysses. It is a realm where the familiar rules of space and time falter, a place perhaps forever cut off from our view, yet one that beckons our imagination and the frontiers of science. Imagine for a moment that you could take an impossible journey, diving straight toward a black hole. At first, as you approach, you'd feel the growing pull of gravity. If the black hole is a smaller one, that pull would stretch you grotesquely long and thin, a fate scientists grimly nicknamed spaghettification. Your body would be drawn out into a strand by the tidal forces, with gravity tugging harder on your feet than your head. until even molecules could be torn apart. For a larger, supermassive black hole, the gradient in gravity might be gentler, and you might drift past the point of no return without immediate calamity. Either way, once you cross the event horizon, the outside universe would see you no more. To a distant observer, you would appear to slow and fade, frozen at the threshold. But from your perspective, you fall onward, carried by spacetime into the heart of darkness. For you, there is no turning back on this one-way voyage into the unknown. Crossing the event horizon, reality would grow stranger still. From your vantage point, the outside universe would appear to fade and distort above you, as if seen through a shrinking, bright window. Light from the stars behind might bend around, smearing into a halo of ghostly traces encircling the blackness. Every direction ahead leads deeper inward, and nothing from outside can reach you now. You are falling toward whatever lies at the ultimate end of gravity's pull. What lies within that darkness? According to Einstein's general relativity, the journey can only end in one place: the singularity. This is the very core of the black hole, a point, or in the case of a spinning black hole, perhaps a ring, of infinite density and zero volume, where the pull of gravity is beyond extreme. At the singularity, the known laws of physics break down completely. Space and time themselves become tangled and nonsensical. In a sense, the singularity is a wall in our understanding, a place we can describe only with mathematics that yield infinities, a clear sign that our equations have reached their limits. It's as if nature has drawn a curtain, and beyond it lies a realm we are not yet equipped to describe. This singularity remains a stark reminder that here our knowledge meets a wall, and beyond it, only speculation can roam. The existence of a singularity poses one of the greatest challenges to modern physics. We believe that a new kind of physics, a unified theory of quantum gravity, is needed to peer behind that curtain. In the 1970s, Stephen Hawking made a startling discovery by applying quantum mechanics to black holes. He found that black holes should slowly leak energy in the form of what we now call Hawking radiation. Black holes, it turns out, aren't completely black. Over inconceivably long timescales, they radiate and can even evaporate entirely. But this raises a paradox. If a black hole eventually disappears, what happens to all the information about the things that fell inside? According to quantum physics, information about a physical system, the identity of particles, and the details of their state cannot be destroyed. Yet anything that enters a black hole seems to be lost forever beyond the horizon. This conundrum is known as the black hole information paradox, and it has vexed scientists for decades. For now, the information paradox remains an open riddle, a battleground of ideas. It highlights a deep tension between the laws of quantum physics and the theory of general relativity. Somehow, in the heart of a black hole, these two great pillars of science must converge. But exactly how remains one of the great unanswered questions of our time. Until a resolution is found, the fate of information swallowed by a black hole continues to provoke debate and wonder. Various ideas have been proposed to resolve the paradox, each intriguing but unproven. One suggestion born from string theory and holographic principles is that the information isn't lost at all. Instead, it might be encoded on the event horizon itself, like a cosmic hologram. In this view, the surface of the black hole could hold a kind of record of everything that has fallen in, preserving information even as the black hole radiates away. Another proposal is that when a black hole dies, it might leave behind a small, exotic remnant or trigger some other transition that carries away the information. Some have speculated about a firewall, an intense burst of high-energy particles at the event horizon that could, in theory, destroy information before it ever truly disappears. These ideas remain speculative, and each challenges fundamental assumptions of physics. No consensus has been reached, and each hypothesis is a matter of lively debate. In fact, some recent theoretical breakthroughs hint that information might not be lost after all, that subtle correlations in the radiation, often discussed in terms of a page curve, could allow a black hole's secrets to eventually leak back out. What we do know is that resolving these mysteries will require a marriage of the very large and the very small, a theory that unites gravity with quantum mechanics. Scientists around the world are working on this problem under many banners: string theory, loop quantum gravity, and other approaches. Bit by bit, through thought experiments and clever calculations, they are attempting to chip away at the paradoxes. For many scientists, this is perhaps the most profound problem in physics. For now, the solution remains elusive. But with each step, science inches closer to a theory that can describe even these ultimate extremes. The outcome of this endeavor could revolutionize our understanding not just of black holes, but of space, time, and the fundamental nature of reality. Standing at the edge of what we know, black holes confront us with the limits of human knowledge. They encapsulate some of our greatest triumphs. We predicted their existence, found them in the cosmos, and even imaged their shadows. Yet they also guard some of the deepest secrets still left to uncover. Peering into a black hole is peering into our own scientific horizons. How far can our theories take us, and where do they break? Each question we answer about black holes seems to spawn new puzzles. In a way, black holes are like cosmic mirrors, reflecting back the gaps in our understanding. But these gaps are also doorways to progress. By trying to understand the unknowable interiors of black holes, we drive physics forward into realms it has never gone before. And so, the enigma of what lies beyond the horizon remains. For all we have learned on our journey, from the faint whisper of the cosmic microwave background, to the swirling of galaxies, to the secrets of dark stars and cosmic giants, the heart of the black hole still beckons with unanswered questions. It is a reminder that the universe still holds mysteries as deep as any ocean and as dark as the void itself. In the silence beyond the light, at the threshold of a black hole's abyss, our story pauses, awaiting the next discovery. With each new insight, we push a little further into the darkness, hopeful that one day, perhaps, we will understand what the cosmos has hidden in that ultimate night.